Hello there, and welcome to another quiet night with the Sleepless scientist. Tonight, we'll wander into one of the strangest and most mysterious places the universe has to offer, the hidden heart of a neutron star. If you enjoy this quiet wandering, a like or subscribe would mean a lot. Share where you are and what time it is. It feels like gathering around one fire across the scattered corners of Earth. Now, soften the room. Let a hum keep you company, and let's begin. If you drift off, that's more than fine. The story will still be here, waiting when you return. There is something deeply human about staring at the sky and wondering what lies inside, the things we see but cannot touch. When you look at the sun, you know it is hot, bright and alive with fire. But you also know that behind the glare lies a heart you will never touch. When you look at the stars at night, twinkling softly, you know they are enormous furnaces, holding themselves in a delicate balance that has lasted for billions of years. But there are some stars that go further, stars that have collapsed, cracked, and been forced into a form so extreme that even our best words begin to falter. Neutron stars are not simply stars in miniature. They are matter pushed to the very edge of what physics can allow. Places where atoms surrender, where protons and electrons merge, where gravity wins nearly everything, but not quite. Imagine matter squeezed so hard that mountains become invisible, so heavy that a teaspoon weighs as much as mountains, and so dense that space and time themselves bend tightly around it. A neutron star is not just a remnant of an old life. It is a new experiment written by the cosmos, and yet, for all that we know, the core of a neutron star remains an unopened book. We can weigh them, we can measure their spin, we can even listen to the waves they send through space-time when two of them collide. But the secret at the very centre, the composition of their hidden heart, is still only guessed at. Is it simply neutrons, packed more tightly than any library of physics ever dared imagine? Is it something stranger? Hyperons, meson condensates, quarks swimming free, or perhaps something we do not even have words for yet. Some even whisper about Bose-Einstein condensates, or the presence of dark matter tucked away in a silent partnership. Tonight, we will walk gently toward this mystery. Step by step, layer by layer, we will descend from the ordinary plasma of the sun, past the calm white dwarf stars supported by their crowd of stubborn electrons, to the neutron stars themselves, city-sized remnants, spinning lighthouses, magnetic titans. We will pause at their crusts, where matter arranges itself into strange pasta shapes. We will weigh them through delicate measurements from orbiting telescopes, and then we will dare to imagine what lies inside, exploring the speculative, the radical, and the almost dreamlike possibilities that scientists entertain. But do not worry, this is not a march of formulas or a flood of numbers. This is a slow, careful exploration, guided by metaphors and images you can hold gently in your mind. Think of it less as a lecture, and more as a soft story told around a fire, where every now and then the universe leans in to whisper a strange fact, and then leans back, leaving you free to drift. If your eyes close along the way, that's not a failure, it's the point. The story of neutron stars will carry on whether you're awake or dreaming. Perhaps you're lying in bed right now, in the quiet of your own corner of the night. Perhaps there is a fan humming softly nearby, or the distant sound of traffic, or maybe only silence. Outside, the stars may be hidden by clouds, or glowing faintly in the cold sky. Imagine among those stars one of them no longer burning as it once did, but collapsed into something dense, mysterious, and silent. Somewhere out there is a neutron star, perhaps thousands of light years away, small as a city but holding the mass of the sun, waiting for us to wonder about its hidden heart. In this journey, we will also see how neutron stars connect to some of the deepest questions of science. They test gravity at extremes. They test quantum physics at densities that laboratories on Earth can only mimic for a fleeting instant. They may even hold clues to the great unfinished project of physics, how to bring together general relativity and quantum mechanics, two elegant frameworks that do not always agree. A neutron star is, in a sense, the cosmos pressing a question into matter itself. What happens beyond the limits of our equations? By the time we reach the end of this quiet journey, you will have drifted with me through the layers of stars, from gentle plasma to exotic quark matter, from familiar light to gravitational waves. You may not have all the answers, no one does, but you will carry with you a sense of wonder about these objects, and perhaps, if you're lucky, you will fall asleep before we even get there. So take a deep breath. Let the day slip behind you. Tonight we step carefully, calmly, into one of the deepest mysteries the cosmos offers. What is hidden in the core of a neutron star? If you have ever bent a stick in your hands, perhaps idly while walking through a park, you know the way it resists at first, then creaks a little, and then, with a sudden crack, it gives way all at once. The stick doesn't fail slowly, it holds, and then in an instant it snaps, the stored strain suddenly released in one sharp sound. Nature has many ways of showing us this kind of behaviour, this quiet build-up followed by a sudden collapse. On Earth we see it in avalanches, in earthquakes, in the snapping of a rope that has carried too much weight. In the cosmos, these tipping points are played out on far grander scales, often invisible to us, until they unleash themselves with a brilliance that lights up entire galaxies. Consider the sun. For all its calm glow from our point of view, its surface is restless, churned by magnetic fields that twist and knot like invisible threads pulled too tightly. Most of the time, these tensions remain hidden beneath the surface, but every now and then the magnetic field snaps, releasing energy in the form of solar flares, sudden bursts of light and charged particles thrown out like sparks from a roaring fire. A flare is not a slow leak, it is a sudden tipping point, the system unable to hold its balance any longer. On a larger scale, imagine stars far heavier than our Sun, stars that have burned through their fuel, not in 10 billion years, but in a few million, racing toward exhaustion. These massive stars end their lives in cataclysmic hypernovae, explosions so powerful they can be seen across vast stretches of space. The core of such a star cannot support itself against gravity once the nuclear furnace is extinguished. The outer layers fall inward, rebound, and the result is a blast that outshines galaxies. Again, the pattern is the same, a balance held until it is impossible, and then a sudden, violent release. There are also stranger examples, quieter until the moment they erupt. Magnetars, a rare class of neutron stars, are born already extreme, with magnetic fields 1,000 trillion times stronger than Earth's. Their crusts, although solid, are under constant stress from the twisting of that unimaginable field. At times, the crust gives way in what scientists call starquakes, sudden fractures that jolt the surface and release bursts of X-rays and gamma rays across the universe. To us, they appear as sudden flashes of high-energy light, brief but astonishingly powerful. It is the same story again, just on an alien stage. Pressure builds, the material holds, and then a sudden break transforms stored stress into released energy. These cosmic tipping points are not random. They are reminders that systems, whether small or vast, hold themselves together only so long as the forces at work remain in balance. Gravity pulls inward, pressure pushes outward. Magnetic fields twist and strain. Nuclear fuel burns, holding up a star until it doesn't. Each system has its own quiet agreement, its own equilibrium, and when that contract is broken, the change is never gradual. It comes suddenly in a flash, a quake, a burst, a collapse. It is tempting to think of the cosmos as eternal and unchanging, But these moments remind us that even stars, for all their size and brilliance, can reach breaking points. They live balanced between competing forces, just as bridges sway between wind and support, or as a tightrope walker balances each step. And like those bridges and walkers, when the balance is lost, the shift is abrupt. Neutron stars belong to this family of tipping points, but they are perhaps the most dramatic of all. They are what remains when the balance tips so far that ordinary matter cannot hold itself together, yet not so far that everything disappears into a black hole. They are the safety net just before the final fall, the point at which matter rearranges itself into something new, pressed into forms we cannot replicate on Earth. To understand them, it helps to remember that the universe often writes its most astonishing chapters at the edges, at the moments when one system gives way and another takes its place. The idea of a tipping point can be seen in smaller, everyday things. Think of water as you heat it. For a while it grows warmer, steam rising more quickly, but at one precise temperature, 100 degrees Celsius under our usual conditions, it undergoes a sudden transformation. It boils, becoming vapour, and the change is complete, abrupt, unmistakable. Or think of ice under pressure. Push on it gently and it holds firm, but with enough weight, the crystals reorganize and the ice shifts, sliding in glaciers or breaking apart in ice flows. These are local echoes of the same story. Matter has boundaries, thresholds beyond which it behaves differently. So when we talk about stars breaking their balance, we are not speaking of something alien and unreachable. We are speaking of a pattern that is familiar, one we know from daily life. Systems resisting change until the resistance can no longer hold. The cosmos simply plays this game on scales so vast with energy so immense that they astonish us. As we begin this journey deeper into the story of neutron stars, hold this idea in mind, that stars, like all things, live in balance, and when that balance is disturbed, when the inward pull of gravity grows stronger than the outward push of pressure or field, the result is sudden, transformative, and sometimes violent. Solar flares, hypernovae, magnetoquakes. Each is a different verse of the same song, a song about balance and its breaking. And yet, while these events are spectacular, they are also hints. They show us that the universe does not slide gently past every threshold. Sometimes it leaps, sometimes it snaps, and the neutron star is the most striking leap of all, a collapse that does not end in disappearance, but in a new and stable form, holding secrets in its heart that we still cannot fully read. Soon we will turn to the sun, not in its violent flares but in its ordinary steadiness, to understand how a star holds its balance for so long. For to know how balance is broken, we must first know how it is kept. And in that quiet, luminous ball we see every day, there lies the key to understanding the strange descendants that emerge when balance is finally lost. If you want to understand why stars sometimes break, it helps to begin with a star that, at least on the scale of human lives, almost never does. Our sun, the steady lantern of the day, is not the biggest star in the universe, not the hottest, and not the most dramatic. But it has something that the restless giants and the quickly burning blue stars do not: patience. For over 4 billion years it has held its balance, burning quietly, changing slowly, and providing Earth with a stage on which life could unfold. It is, in many ways, the textbook example of stability, and for that reason it serves as the benchmark for understanding what balance in a star means, and how that balance eventually tips toward extremes. Look closely, though not too closely, for the sun is still a furnace, and you see its outermost layer, the photosphere, glowing at a temperature of about 6,000 degrees Celsius. Here, light escapes into space, and to our eyes it appears as a simple, dazzling brightness. Yet the physics behind this layer is anything but simple. In the photosphere, matter exists in a delicate state between being fully neutral and fully ionized. Scientists describe this transition with something called the Saha ionization equation, which might sound intimidating, but at its heart it is a way of describing how atoms begin to let go of their electrons as the temperature rises. You can picture it less as an equation, and more as a crowd in which people are holding hands tightly when it's cool, but as the heat builds, some begin to drift apart, connections breaking, the crowd becoming looser. At the photosphere, this partial ionization shapes how light moves through the sun, setting the conditions for what we see as sunlight. Deeper inside, the story changes. The material becomes fully ionized plasma, not atoms with neat shells of electrons, but a sea of nuclei and electrons all free to move, colliding constantly. Plasma is not something we encounter much on Earth, apart from lightning, fluorescent lights, or the flame of a plasma torch, yet in the universe, it is the dominant state of matter. Inside the sun, plasma conducts currents, creates magnetic fields, and carries energy outward in a restless dance that continues day after day, century after century. What keeps all of this from collapsing under the sun's immense weight? The answer is balance. On one side is gravity, relentless, pulling every particle inward toward the core. On the other is pressure, not the kind of pressure you feel when squeezing air into a balloon, but the pressure of particles moving at immense speeds, colliding, pushing outward. These two forces are locked in a tug-of-war known as hydrostatic equilibrium, and it is this balance that allows the sun to remain stable. If gravity were to win, the star would contract and heat until pressure pushed back. If pressure were to win, the star would expand and cool until gravity regained its hold. The sun wobbles a little in this dance, but on the whole it holds steady, like a perfectly balanced scale. To measure this balance directly is difficult, but nature gives us a gift: neutrinos. These nearly massless particles are produced in the core as hydrogen fuses into helium, the very process that powers the sun. Neutrinos hardly interact with matter, which means that while photons, the particles of light, may take thousands or even millions of years to drift outward from the dense core, bouncing endlessly, neutrinos leave almost immediately. They pass through the sun, through space, even through our bodies, barely noticing the obstacles. To detect them requires vast underground detectors filled with ultra-pure water or special materials shielded from cosmic rays. Yet when we do detect them, they provide a direct thermometer of the solar core. They tell us that deep inside, where gravity's pressure is most intense, the temperature is about 15 million degrees Celsius. That number is not a guess. It is written in the stream of neutrinos arriving every second from the heart of the sun. This combination, hydrostatic equilibrium measured through pressure and neutrinos serving as witnesses, makes the sun a natural laboratory for what scientists call the equation of state, or S. The phrase sounds abstract, but it simply refers to the relationship between pressure, temperature, and density in matter. On Earth, we use similar equations to describe how steam engines work, or how gases behave in a cylinder. In stars, the EOS is the rulebook that says how much pressure a certain density of hot plasma will produce, and in turn how gravity and that pressure balance. Because the sun is so well measured, it becomes the benchmark. If our equations cannot describe the sun, they cannot be trusted to describe anything stranger. There is a calm reassurance in knowing that our own star is, for now, firmly within the grasp of this balance. When you step outside and feel its warmth on your face, you're experiencing the outward push of pressure, keeping pace with the inward pull of gravity. A quiet tug-of-war that has remained almost unchanged since the first humans looked up and wondered. And while the sun will one day exhaust its hydrogen fuel and drift into the next chapter of its life, becoming first a red giant and later a white dwarf, that moment is billions of years away. For now, it is the perfect example of how stars can hold themselves together. To rest with this thought for a moment is soothing, that even in a universe where stars explode, where matter collapses, and where sudden tipping points light up, the night, there is also steadiness, a star that rises each morning and sets each evening, a star that for generations has been as reliable as the passing of time itself. And yet, in the shadow of this steadiness, we're reminded that not all stars are so patient. Some are larger, some are more fragile, and some are destined to collapse into neutron stars, places where the very equation of state we trust in the sun will be tested to its breaking point. So as we continue, let the sun serve as our baseline, the calm before the collapse, the standard against which we measure all extremes. It is the quiet rhythm to which other stars, more turbulent and short-lived, are compared. In its steadiness lies the reference, and in the contrast to its steadiness lies the mystery that drives us forward. For if the sun is the teacher of balance, neutron stars are the test, and the lessons we learn from them may well reshape our understanding of matter and of gravity itself. When the life of a star like our sun draws to a close, its balance is no longer quite so easy to maintain. The fuel that once fewed so steadily in the core becomes scarce, the furnace sputters, and gravity begins to tug more insistently. The star swells into a red giant, shedding its outer layers into space in shimmering shells of gas, until at last what remains is not a blazing beacon, but a compact ember. This ember, no larger than Earth yet containing more mass than the sun's core, is called a white dwarf. To us it may look faint and small, but inside it is the stage for one of the strangest kinds of balance in the universe. The story of white dwarfs is not only astrophysical, but also deeply human, tied to the minds of scientists puzzling through the question, how could such an object exist? In the early 20th century, when observations revealed stars that were faint yet incredibly dense, astronomers like Ralph Fowler and Eddington debated what kind of pressure could possibly support them. The key came from a principle introduced by Wolfgang Pauli, one that sounds abstract at first but can be imagined in quite ordinary terms. The Pauli exclusion principle says, quite simply, that no two identical fermions, particles like electrons, can occupy the same quantum state at the same time. Imagine, if you will, a crowded theatre, where every seat can only hold one person, and where no two people can ever sit in exactly the same spot. At first, the crowd spreads out comfortably, filling the seats closest to the stage. But as more arrive, the rules force them to sit further back, higher up in the balconies, each seat unique. In a star, gravity is the usher, relentlessly forcing more people into the theatre, but the electrons resist. They cannot all squeeze into the lower seats, so they climb into higher and higher energy levels. This climbing, this resistance, is what we call electron degeneracy pressure. Unlike the pressure we know from gases, which comes from heat and motion, degeneracy pressure arises from pure quantum rules. Even if the star is cold, the electrons cannot all pile into the lowest possible states. They must fill the available quantum seats one by one, and in doing so they push back against gravity. This is not the kind of pressure you feel when inflating a balloon, or when pressing your hand against a wall. It is quieter, stranger, a kind of invisible stiffness written into the very structure of matter. White dwarfs, then, are balanced not by burning fuel, but by this peculiar quantum rule. Imagine holding a balloon filled not with air but with pure rules of physics, the Pauli exclusion principle forming the skin. It is not something you can puncture or deflate, it simply exists, holding the star up against collapse. For a time, this balance is enough. A white dwarf can persist for billions of years, cooling slowly, glowing faintly, until eventually it becomes a black dwarf, dark and silent. But not all white dwarfs remain safe. The principle that saves them also sets a limit, and that limit would be uncovered by a young scientist on a long ocean voyage. Subramanian Chandrasekhar, travelling from India to England in the early 1930s, calculated that above a certain mass, about 1.4 times that of our Sun, The degeneracy pressure of electrons could no longer resist gravity. The theatre of seats, no matter how many balconies you built, could not accommodate more. The crowd was too heavy, the usher too insistent, and the rules gave way. This mass became known as the Chandrasekhar limit, and it remains one of the most important thresholds in astrophysics. Below it, stars can collapse into white dwarfs and live out long, quiet afterlives. Above it, the balance fails, and something more extreme must happen. The electrons are forced to combine with protons, creating neutrons, and the star collapses further, shrinking from Earth-sized to city-sized, a neutron star. The elegance of this discovery lies not only in its mathematics, but also in its simplicity. The same principle that tells us electrons cannot all sit in the same state, the same rule that explains the structure of atoms, also explains the fate of stars. A law that applies in the tiniest corners of matter, in quantum mechanics, is also the law that governs suns and their deaths. There is a kind of poetry in that, the small and the vast bound by a single thread. For our purposes tonight, what matters is that white dwarfs show us the first step in the ladder of collapse. They are a demonstration of how matter resists, of how even when nuclear furnaces go out, there is still a kind of stubbornness in the fabric of the cosmos. But they also hint at the limits of that resistance. For every rule that holds the universe together, there comes a point where gravity grows stronger still, where balance shifts again, and where a new and stranger object must take the stage. To picture a white dwarf, you might imagine the embers of a campfire at night, still glowing long after the flames have gone. Or you might imagine a diamond, a vast crystalline carbon sphere, since some white dwarfs may in fact be made largely of crystallized carbon. These images are calm, soothing even, and yet behind them is the quiet roar of quantum laws resisting collapse. As you let this thought settle, consider that somewhere in the galaxy, white dwarfs drift silently, the remains of stars that lived and died before our sun was even born. They are ancient reminders of balance held by rules invisible to our senses, and beyond them, waiting, are the neutron stars, denser, stranger, more extreme, that appear when even the crowd of electrons can no longer resist the ushering force of gravity. Every balance in nature has a limit, and every rule that holds the world together eventually meets the point where it bends too far. White dwarfs, for all their strange quantum resilience, are no exception. The Peale exclusion principle may be firm, the theatre of seats may stretch up into higher and higher balconies, as electrons are forced into greater energy levels, but even that cosmic auditorium has a capacity. Add too many guests, and there comes a moment when the structure cannot bear the weight. That moment, perched between survival and collapse, is what we call the Chandrasekhar limit. The story of this limit has become legend in astrophysics, partly because of the image of Chandrasekhar himself, a young man only in his 20s, sailing from India to England with little more than books, paper, and an eagerness to calculate. On that voyage, he worked out what would happen to a white dwarf as its mass increased. While many might have enjoyed the sea breeze or stared at the horizon, Chandrasekhar's gaze was turned inward to the mathematics of collapsing stars. He found that when the mass of a white dwarf exceeds about 1.4 times the mass of our Sun, electron degeneracy pressure is no longer sufficient to balance gravity. The crowd of electrons cannot keep pushing back, and gravity wins. This was a controversial conclusion at the time, even unsettling. To many senior scientists, the idea that a star could collapse beyond white dwarf status seemed absurd, a kind of theoretical overreach. Arthur Eddington, one of the most respected astronomers of the day, dismissed Chandrasekhar's result, perhaps unable to accept that the universe might allow such radical ends for stars. And yet, as time passed, evidence and theory converged. Chandrasekhar's limit was not only correct, it became a cornerstone of our understanding of stellar evolution. But what does it mean in practice? Imagine once again that theatre of electrons. At first, everyone finds a seat, however cramped, and the crowd grows restless but stable. Then, more and more people are forced in, until every seat is taken and there is no more room. Gravity, the usher, continues to push, and the only option left is that the very rules of seating must change. In the heart of an overfed white dwarf, electrons are pressed so tightly against protons that they merge, creating neutrons. The ushers do not stop. They simply rewrite the arrangement of matter. At this tipping point, the white dwarf cannot remain what it was. The collapse deepens, and in an instant the scale changes dramatically. The star, once the size of Earth, shrinks to the size of a city. The density, already extreme, becomes staggering, surpassing even the density of atomic nuclei. The outer layers are cast off in a supernova, a final outburst of light, while the core contracts inward, leaving behind a neutron star. To stand at the edge of this limit in your imagination is like standing on the brink of a cliff, staring into a fog you cannot see through. On one side is stability, white dwarfs glowing faintly for billions of years, cooled embers scattered across the galaxy. On the other side is collapse into the unimaginable, neutron stars exotic and compact, or, if the mass is greater still, black holes from which not even light can escape. The Chandrasekhar limit is the line drawn across that boundary. It is helpful perhaps to compare this to more familiar thresholds. Think of water. It remains liquid as you heat it, rippling and restless until the temperature reaches 100 degrees Celsius. At that moment, it boils, turning to vapour. The change is not gradual. It is a sudden transformation, governed by the rules of physics. Or think of ice on a frozen river, strong under the weight of skaters and sleds, until the day the temperature rises and the structure weakens. The collapse is not a matter of choice, but of laws. The Chandrasekhar limit is the astrophysical equivalent, a boiling point for matter's resistance. When astronomers look at Type Ia supernovae, explosions triggered when a white dwarf steals matter from a companion star until it passes the limit, they are seeing this cliff in action. These supernovae shine with such consistent brightness that they have been used as cosmic mile markers, helping us measure the expansion of the universe itself. In that way, the failure of balance in a star has given us one of the most reliable tools for mapping the cosmos. A collapse, paradoxically, becomes a beacon. And yet, for all the grandeur of this moment, there is something quietly inevitable about it. Gravity does not rush. It waits. It waits as stars live their long lives, as hydrogen fuses into helium, as white dwarfs cool across eons. And then, when the mass grows just a little too heavy, when the threshold is crossed, gravity steps forward, patient, inexorable, and the star changes forever. To think of it this way is strangely calming. The universe does not make mistakes. It follows its rules, and those rules have thresholds. The Chandrasekhar limit is not a disaster, it is a door. Beyond it lie neutron stars, objects that carry us closer to the edge of physical law. They are the next step in matter's journey, the next attempt of the cosmos to answer the question, how much weight can the fabric of existence bear before it gives way to something new? So as we step from white dwarfs to neutron stars, remember the cliff. It is not only a number in equations, but a boundary in nature, one we can picture in metaphors of cliffs, boiling water, or crowded theatres. Beyond it, balance changes. Beyond it, matter reshapes itself, and stars, once steady and familiar, become something entirely different. When the core of a massive star collapses beyond the safety of white dwarf physics, the result is something so strange that even seasoned astronomers struggle to describe it without pausing, without reaching for metaphors, as though words themselves hesitate at the threshold. The star, once vast and radiant, becomes a remnant no wider than a city, yet still weighing more than our Sun. It is as if the entire population of Earth, and then some, were compressed into the space of a single teacup, their mass unchanged, but their form utterly altered. This is a neutron star, a monument to gravity's triumph and matter's reluctant surrender. To begin to picture it, imagine a sphere about 20 kilometres across, roughly the distance of a daily commute in a small city. 20 kilometres may sound large when walked on foot, but on the scale of stars it is minuscule, a fragment. Our Sun, by comparison, spans over 1 million kilometres in diameter, and yet a neutron star can contain the same amount of mass, sometimes more. To hold a teaspoon of its material would mean holding billions of tons, enough to outweigh mountains, enough to crush steel like paper. And of course, you could not hold it at all. The gravity would tear your arm, your body, the very atoms of your hand apart before you even reach the surface. The surface of a neutron star is not like the ground we stand on. It is more like a thin, iron-hard crust resting on seas of nuclear matter. Gravity there is 100 billion times stronger than Earth's, so strong that mountains can rise only a few millimetres before they collapse under their own weight. If you could somehow stand there, a thought experiment more than a possibility, you would weigh more than entire skyscrapers, pressed into the crust like a feather into granite. Light itself bends under such gravity, curving back toward the surface, so that an observer above might see more than half of the star at once, the horizon curved upward into view. These stars are not quiet. Many spin at incredible speeds, sometimes hundreds of times per second, rotating with a steadiness that rivals the finest clocks. These are pulsars, neutron stars whose beams of radiation sweep across the sky like the beams of a lighthouse. When one of these beams crosses Earth, we detect a pulse of radio waves or X-rays, arriving again and again with almost unimaginable regularity. Some pulsars are so precise that they outdo atomic clocks, their rhythm never faltering even over decades. Imagine the tick of a clock so reliable that entire networks of satellites could synchronize themselves to it. And indeed, pulsars have been proposed as cosmic beacons for interstellar navigation, lighthouses not only for astronomers but perhaps one day for spacecraft. Among them, the Crab pulsar stands as one of the most famous. Born from a supernova recorded on Earth in the year 1054, when Chinese astronomers saw a new star appear in the sky bright enough to be seen in daylight, it still spins more than 30 times per second, 1,000 years later. Around it lies the Crab Nebula, a cloud of gas and dust glowing in vivid colours, illuminated by the pulsar's energy. To look at an image of the Crab Nebula is to see a monument frozen in time, the ghost of a star's death and the relentless heartbeat of its collapsed core, still pulsing with energy across centuries. The existence of such objects forces us to rethink our sense of matter itself. On Earth, we're used to the idea that matter is mostly empty space, atoms with nuclei tiny at their centres and electrons drifting far around them, like fireflies in a cathedral. In a neutron star, that space is gone. The electrons have merged with protons, leaving behind neutrons packed shoulder to shoulder, as if the cathedral had collapsed and all the fireflies were pressed together into a single solid block. The result is a density so high that the distinction between particle and mass blurs, where physics begins to resemble poetry, speaking of matter as if it were both fluid and solid, rigid and yielding. And yet, for all this strangeness, neutron stars are not exotic curiosities hidden beyond reach. They are real, measurable, observable. Their pulses reach our radio telescopes, their bursts of X-rays flash across our detectors, their gravitational tug on companion stars reveals their mass. They may be far away, thousands of light years across space, but their influence reaches us nonetheless. The light from the Crab pulsar, for example, has travelled across centuries of emptiness, crossing the gulfs between stars, to arrive at our telescopes and whisper the news of its relentless spin. To think of them this way is to feel both small and connected. A teaspoon of neutron star matter might crush us, but the information they send, the light, the pulses, the waves, arrives gently, harmlessly, like rain tapping on a window. We can sit in our quiet rooms wrapped in blankets and listen to their story without fear, receiving signals from some of the densest objects in the universe as easily as one might hear the tick of a clock in the dark. Neutron stars, then, are not only monuments to collapse but also messengers. They remind us that matter can survive incredible strain, that balance can be rewritten in unfamiliar ways, and they show us that even at the edge of physical law, the universe has found a form of stability. White dwarfs resist with electrons. Neutron stars resist with neutrons. Beyond them lies only the black hole, where no form of matter resists at all. But here, in the realm of neutron stars, the story is not yet finished. The cliff has been crossed, but the fall has not ended. Instead, we find a new plateau, solid, bizarre, and waiting to be explored. As we rest in the glow of this understanding, picture again that teaspoon, impossibly heavy, impossibly dense, and yet still a piece of the same matter that makes up you, your body, your chair, the air you breathe. The difference is only in the pressure, in the way gravity is squeezed and squeezed until the ordinary became extraordinary. That, perhaps, is the most humbling thought. Neutron stars are not made of something alien. They are made of the same matter we are, only the conditions are changed. The pressure so great that atoms themselves have given way. And so, as we move forward in our quiet exploration, remember this. The next time you stir your tea, glance at the spoon. It is an ordinary spoon, ordinary matter, but in some distant corner of the galaxy, a teaspoon holds the weight of mountains. If the sheer density of neutron stars was not enough to leave us breathless, their behaviour once they are born carries another layer of strangeness. They do not simply sit in silence, glowing faintly and slowly cooling across eons. Many of them spin, and not just in the way the Earth rotates once a day, but with a speed so astonishing that it borders on the incomprehensible. Imagine holding a ball the size of a city, filled with more mass than the sun, and watching it rotate dozens or even hundreds of times every second. These are pulsars, the whirling lighthouses of the cosmos, and through their beams we receive some of the most regular signals in the universe. To understand how they shine, picture a lighthouse on a foggy shore. The beam of light does not illuminate every direction at once. Instead, it sweeps around in circles, sending a flash toward anyone standing in its path each time it turns. Pulsars work in much the same way. As they spin, intense magnetic fields channel radiation into beams, which sweep through space like invisible searchlights. From Earth, when one of these beams crosses our line of sight, it appears as a pulse of radio waves or X-rays, arriving again and again with such precision that entire observatories are timed by their rhythm. Some pulses are so steady that their ticks could rival the quartz crystals in our watches, or even the atomic clocks that define the second itself. The first pulses discovered in the 1960s were so regular that the scientists who observed them briefly wondered whether they might be artificial, signals from some distant intelligence. They even gave them the tentative nickname LGEM, for little green men. Of course, the explanation was natural rather than alien, but the wonder has never faded. Each pulse is the heartbeat of a collapsed star, announcing across the cosmos that balance has been remade in an extraordinary way. The speed of these stars is not an accident. When a massive star collapses into a neutron star, it shrinks dramatically, and in doing so it spins faster, much like a figure skater pulling in their arms. Conservation of angular momentum, a principle as old as Newton, ensures that what begins as a slow rotation becomes dizzyingly fast as the radius contracts. What once was the stately spin of a star larger than the sun becomes the frantic whirl of a neutron star, stable, relentless, and astonishingly precise. But not all neutron stars behave with the neat rhythm of pulsars. Some push the extremes even further, developing magnetic fields of unimaginable intensity. These are magnetars, and while they may look like pulsars at a glance, they are far more volatile. Their magnetic fields can be 1,000 trillion times stronger than Earth's, strong enough to distort the shapes of atoms themselves, strong enough to pull on the very vacuum of space. If a magnetar were placed halfway between the Earth and the Moon, its field would be strong enough to erase every credit card on Earth in an instant. It is an almost comical example, but it hints at the scale of their influence. Such fields do not remain calm. They twist and strain, storing energy in the crust of the star until, at last, the crust can no longer endure. Then comes a starquake, a sudden crack in the neutron star's rigid shell, releasing a burst of radiation so powerful it can be detected across galaxies. In 2004, a magnetar called SGR 1806-20 released a flare so intense that it briefly overwhelmed detectors on Earth, despite being 50,000 light-years away. For a fraction of a second, it outshone the rest of the Milky Way combined. It is humbling to think that the quiet crack of a crust, deep in space, can send such an echo across the cosmos. And yet, for all their ferocity, magnetars are still balanced in their own way. They are reminders that even within the realm of neutron stars there are gradations of extremity. Some settle into the calm rhythm of pulsars, spinning down slowly over millions of years. Others strain under magnetic fields so intense that their stability is punctuated by sudden bursts, earthquakes on a stellar scale. The diversity of their behaviour is a sign that even when matter has been squeezed to the limits of physics, nature still finds many ways to express itself. To think about these stars is to stand again at the edge of wonder. Imagine hearing the tick of a pulse arriving at your radio telescope every fraction of a second, unbroken, unhurried, precise as the ticking of a metronome. And then imagine, across the sky, a magnetar flashing like a camera bulb, sudden, blinding, a reminder that balance in such places is never guaranteed for long. Together, they are like two instruments in the same cosmic orchestra, one providing the steady beat, the other striking the cymbals with unpredictable brilliance. From Earth, these signals arrive faintly, whispers carried across light years, but to us they are invaluable. They tell us not only that neutron stars exist, but also how they live, how they spin, how they strain under their own magnetic weight. They are windows into the physics of matter at its most compressed, laboratories in the sky that experiment endlessly without our intervention. As we continue deeper into the story, we will leave the surface with its beams and its quakes, and descend beneath the crust, where matter organises itself in patterns stranger still. But before we do, pause for a moment on the thought of these stars, compact, spinning, magnetic, pulsing across the universe with signals so steady that they could guide ships, and so violent that they could outshine galaxies. They are reminders that the cosmos, though vast, has a heartbeat, sometimes calm and sometimes wild, but always carrying the rhythm of balance remade in the most extreme ways. If we could peel back the surface of a neutron star, not with drills or shovels, but with the kind of gentle imagining one might use when opening a storybook, we would find layers that are neither quite solid nor quite liquid, but something in between, a structure at once familiar and alien. The surface, though often described as crust, is not like the crust of bread or the rocky crust of Earth, but more like a metallic shell forged under pressures that defy every material we know. Just a few centimetres thick, it can withstand stresses stronger than steel, its atoms compressed until they resemble a tightly packed mosaic of nuclei and electrons. As you sink deeper, gravity presses harder, and the atoms themselves can no longer remain intact. At some depth, the pressure is so intense that electrons are squeezed directly into protons, creating neutrons, and those neutrons begin to drip out of the nuclei like water leaking from overfilled buckets. This region is called, quite poetically, the neutron drip zone, and it marks the beginning of matter reshaping itself into something we do not see anywhere else in the cosmos. It is the first signal that the ordinary architecture of atoms, so dependable in our daily lives, has begun to collapse under the weight of stellar gravity. But the story does not end with this dripping of neutrons. As one goes further, the nuclei themselves begin to twist and contort under the unrelenting squeeze, no longer able to remain in neat, round shapes. Instead, they stretch, merge and reassemble into patterns that sound almost whimsical when described, yet are backed by some of the most serious calculations in nuclear physics. Scientists call them nuclear pasta, not as a joke but as an honest attempt to find words that capture their shapes. In these depths, matter may arrange itself into spheres like gnocchi, rods like spaghetti, or sheets like lasagna. It is as though the universe, unable to hold atoms in their familiar structures, invents a new cuisine of matter, delicate lattices balancing between the forces that hold nuclei together and the crushing pressure of gravity. This pasta is not something you would eat, of course, nor would you even recognize it if held in your hand, though holding it is impossible. Instead, it is a way of describing how the ingredients of matter, protons and neutrons, compromise under tension, creating shapes that minimize their energy while still resisting total collapse. In the stillness of your imagination, you might picture it as a frozen feast hidden inside the star, a strange banquet laid out not for taste but for survival. The laws of physics serving as chefs and gravity as the relentless diner demanding more. Yet even this is not the end. Beneath the pasta layers lies something stranger still. A sea of neutrons freed from nuclei, flowing together in a way that defies the usual rules of fluids. On Earth, when we think of a fluid, we think of water running through a stream, or honey sliding slowly from a spoon, always losing some energy to friction, always encountering resistance. In the heart of a neutron star, however, neutrons may form what physicists call a superfluid, a state where they flow without friction, gliding endlessly without slowing. Imagine pouring a cup of water into a bowl and watching it swirl forever, never stopping, never settling, the motion endless and smooth. That is what happens inside neutron stars, rivers of neutrons running without resistance, silent and eternal. The existence of this superfluid is not merely a poetic fancy. We know of it because pulsars, those spinning neutron stars, sometimes behave in curious ways. Every so often their steady rhythm falters, just for a moment, speeding up unexpectedly in what scientists call a glitch. These glitches are thought to be caused by the interaction between the rigid crust and the flowing superfluid beneath it, as if the rivers of neutrons suddenly tugged against their container and jolted the star's rotation. The effect is tiny when measured here on Earth, a fraction of a second. But across the galaxy it reveals the presence of a hidden world, a river flowing beneath a crust of unimaginable hardness. To sit with this image is to feel a kind of quiet awe. Above, a pulsar sweeps its beams across the night sky, steady as a lighthouse. Beneath that surface, layers of matter twist themselves into gnocchi and lasagna shapes, while rivers of neutrons glide forever in silence. It is a hidden choreography, one we cannot see directly, yet one that reveals itself in pulses and glitches, in the patterns of light that reach us from light years away. In our everyday lives, it is hard to picture something so alien, but perhaps we can borrow small comparisons. The neutron drip zone is like the moment when water leaks from an overfilled glass. The nuclear pasta is like the patterns of dough on a kitchen table, though made of protons and neutrons instead of flour. The superfluid is like a dream of water that never stops flowing, an endless loop in which friction has been forgotten. These images are not precise, but they are enough to let us hold the idea gently, to carry it without strain. And so, as we linger here beneath the surface, we begin to see how neutron stars are layered like onions, each layer stranger than the last, each one a response to pressure so immense that atoms themselves must reinvent their form. This crust, with its pasta and its rivers, is only the beginning. Deeper still lies the core, the place where speculation grows bold and imagination strains, where quarks and hyperons, and perhaps even darker forms of matter, may dwell. But before we descend there, it is worth pausing to appreciate this quiet banquet of matter, this frozen flow, this hidden architecture. It is in its own way beautiful, a star that cracked and collapsed, now holding within itself patterns more intricate than lace, rivers smoother than silk, balance remade under conditions so fierce that words falter. And yet here we are, whispering about it across the quiet of night, folding the unimaginable into metaphors we can cradle in our thoughts. It is one thing to imagine a neutron star in broad strokes, a city-sized sphere with the weight of a sun, crusts of nuclear pasta, and rivers of superfluid matter. But to truly test our ideas, we need to know something very simple, and yet very difficult. Just how massive these stars are, and just how large they remain under that mass. In other words, we must weigh and measure them. Tasks that sound straightforward until you remember that these objects are thousands of light years away, glowing faintly, distorted by gravity, and far too dense for any ordinary scale or ruler. And yet, somehow, astronomers have learned to weigh shadows and to measure outlines against the blackness of space. The first clue comes from the way neutron stars tug on their companions. Many of them exist in binary systems, paired with ordinary stars, and as they orbit one another, gravity reveals itself through motion. By studying the way the companion star moves, the Doppler shifts in its light, the rhythm of its orbit, astronomers can infer the weight of the neutron star pulling it. It is not unlike watching two dancers from a distance. By seeing how one leans, how the other is pulled, you can tell how much weight each is carrying, even if you cannot step onto the floor yourself. But weight alone is not enough. To understand what lies inside a neutron star, we also need to know its radius. The radius tells us whether matter at such densities compresses easily, like a sponge squeezed under pressure, or resists fiercely like steel. A soft equation of state allows a star to shrink smaller as mass increases, while a stiff equation resists compression, keeping the star larger. It is in this tension, between soft and stiff, between sponge and steel, that the real secret of the core hides. This is where NICER enters the story, a modest-sounding experiment with a delicate purpose. The Neutron Star Interior Composition Explorer, perched on the International Space Station, is not a massive telescope staring deep into galaxies, but a compact instrument tuned to X-rays, the high-energy light that neutron stars emit as their magnetic fields funnel particles onto their surfaces. By watching how these X-rays pulse as the star spins, NICER can do something extraordinary. Map the surface, measure the hotspots, and reconstruct the star's size and shape. Imagine holding a spinning ball with a glowing mark on it, like a flashlight taped to its surface. As the ball turns, the glow flashes toward you and then away again, brightening and fading with each rotation. From the pattern of those flashes, the timing, the intensity, the shape, you can deduce not only the rotation speed, but also the size of the ball, the way its surface curves, even how gravity bends the light as it leaves. This is exactly what NICER does. Though the ball is thousands of light years away, the glowing marks are magnetic hotspots, and the bending of light is caused by gravity so intense that even beams curve noticeably as they escape. Among the most striking measurements came from a neutron star named J0740 plus 6620, a pulsar about 3,000 light-years from Earth. It weighs more than twice the mass of our Sun, and yet NASA found that its radius was not as small as many soft equations of state predicted. In fact, it seemed surprisingly large, suggesting that the matter inside was stiffer than some theories allowed. This finding rippled through astrophysics, challenging models that assumed exotic cores of quarks or hyperons that would soften the star. Instead, it hinted that the matter within might be holding out more stubbornly, resisting compression like a spring wound tighter than expected. To think of measuring such a star is to appreciate the subtlety of science. There is no cosmic yardstick, no giant scale. There are only beams of light pulsing across space, bent and stretched by gravity, arriving at instruments orbiting Earth. From those faint clues, astronomers deduce the mass, the size, and the stiffness of matter at densities 1 trillion times greater than water. It is, in a sense, like listening to an echo in a cave, and from its tone reconstructing the shape of the cavern, the thickness of the walls, and the weight of the mountain above. These measurements matter not only for curiosity, but for physics itself. The mass and radius together define a point on the great map of the equation of state. Each new neutron star observed is another pin on that map, narrowing the possibilities, ruling out theories, and guiding us toward the truth. In the case of J0740 plus 6620, the point fell outside many expected regions, pruning away entire families of models. The effect is not dramatic to the eye. It does not explode like a supernova or flash like a magnetar-quake. But it is dramatic in thought, shifting our understanding with quiet persistence. To rest with this for a moment is to realize how strange it is that so much of science depends on such delicate signals. The Crab pulsar pulses brightly, but most neutron stars send whispers, faint beams arriving after journeys across light years, stretched and weakened by space. And yet those whispers are enough, when heard with patient ears and clever instruments, to reveal the stiffness of matter itself. It is as though the universe has given us a puzzle box with no direct instructions, only faint knocks from within, and by listening carefully we learn the shape of what is hidden inside. And so, with NICE's measurements, we are brought to the edge of the mass radius puzzle, a quiet but powerful mystery. Neutron stars may not be sponges or steel, but something in between. Something we must describe with equations yet softened by metaphors. The more we weigh and measure them, the closer we come to understanding what lies beneath their crusts. And still, the heart of the matter remains hidden, daring us to listen more closely, to map more carefully, to trust that in shadows and pulses the truth is waiting. When we speak of stiffness in the context of stars, it may sound like an odd choice of word. We think of stiffness in terms of backs after long work, or clothes dried too long in the sun, or springs that resist when pressed. But in astrophysics, stiffness is not about muscles or fabrics. It is about how matter responds to being squeezed. A soft equation of state means that matter yields easily to pressure, collapsing into smaller and smaller radii as weight is added. A stiff equation means matter resists, pushing back, holding its shape, keeping the star larger despite the gravity that tries to compress it. This contrast, softness versus stiffness, forms the core of the neutron star mystery. Imagine holding two cushions. One is feather-filled, and when you press your hand into it, your palm sinks deeply, the cushion flattening under the weight. The other is firm foam, and when you press, it hardly gives, holding its form. Neutron stars are, in their own way, cosmic cushions, except the hand pressing on them is gravity itself, relentless and unimaginably strong. Whether the star is soft like feathers or stiff like foam tells us what the matter inside really is, and the only way to know is to measure both the mass and the radius. The puzzle deepens because neutron stars are not simple. If they were made only of neutrons and protons compressed to absurd densities, we might expect a certain stiffness, a certain relationship between mass and radius. But when astronomers measured stars like J0740 plus 6620, they found something intriguing. The star was heavier than expected, yet not as small as soft models predicted. It seemed to be holding out, resisting compression, a sign of stiffness in the equation of state. That resistance, quiet and invisible though it may be, carried consequences. It suggested that not all the exotic ideas, cores made entirely of quark matter or populated with hyperons, could be right, for such cores would soften the matter, letting the star shrink more than the data allowed. In other words, stiffness was not just a property, it was a clue. It pointed away from some theories and toward others. It told scientists that inside the neutron star, matter might still be organised in ways closer to the familiar, albeit at densities far beyond anything we can recreate on Earth. The softness of quark soup, the pliability of hyperon-rich matter, seemed less likely if stars could stay so large while holding so much mass. And yet the story is not settled. Some models propose that stars may be stiff up to a point, and then soften dramatically in their cores, hiding quark matter in the deepest interior while still appearing stiff overall. Others suggest hybrid stars with layers of stiffness and softness, the outer regions resisting like foam, while the innermost heart yields like feathers. This blending of behaviours makes the puzzle even harder, because the signals we see, mass, radius, pulses, must be interpreted not as simple answers but as mixtures, whispers from layers we cannot peel apart. To picture this, think of a suitcase packed with clothes. At first you fill it with sweaters thick and stiff, and it resists your attempts to close it. Then you press in socks and shirts, which compress easily, and suddenly the suitcase shrinks down further than before. From the outside you see the overall shape, but inside the stiffness and softness mingle. Neutron stars may be similar, with outer layers stiff, inner cores soft, the whole star a compromise between resistance and yielding. The consequence of this puzzle stretches far beyond neutron stars themselves. The stiffness of matter at nuclear densities informs our understanding of fundamental physics, of how the strong force binds protons and neutrons, of how quantum chromodynamics behaves when pushed to extremes. It even touches cosmology, because the same rules that govern matter in neutron stars echo in the early universe, when densities and temperatures were equally intense. To pin down stiffness is not just to describe stars, it is to glimpse the rules of the cosmos written in their most condensed form. And still, as with so many things in astronomy, the answers arrive gently, through measurements of pulses and shadows, through gravitational waves from distant mergers, through whispers carried across space. There is no single laboratory where we can compress matter to these densities and watch it behave. The neutron star itself is the laboratory, and the only way we participate is by listening to its signals, by comparing models, by leaning closer to echoes of light and waves of space-time. To pause here is to appreciate the beauty of such indirect knowledge. It is like listening to a closed piano, hearing only the vibrations of the wood, and from that sound deducing the arrangement of strings inside. The puzzle of stiffness is not solved yet, but each measurement narrows the options. Each new star prunes away possibilities, until one day the equation of state may be revealed in full. Until then, we rest with the tension. Stars heavier than expected, larger than predicted, soft models under strain, stiff models holding on. It is a reminder that matter, like people, does not always behave as expected when under pressure. Sometimes it yields, sometimes it resists, sometimes it does both, depending on where you look. Neutron stars embody this truth at scales that dwarf imagination. Yet the principle is familiar, the same as cushions beneath your hand, or suitcases that resist until they don't, or springs that bend and then snap back. The puzzle of stiffness is both cosmic and ordinary, both grand and intimate. and in that balance lies its quiet power. After all the speculation, all the whispers of quarks and condensates and exotic guests rearranging themselves in the shadows, it is worth pausing at the most modest possibility, the one that asks the least of our imagination, and instead extends the ordinary into the extreme. Perhaps, some scientists suggest, the core of a neutron star is not filled with hidden new forms of matter at all. Perhaps it is simply what it says on the tin: neutrons, packed shoulder to shoulder, with a scattering of protons and a sea of leptons, electrons and their ghostly cousins, the neutrinos, threading through the mix. This is the familiar core, the default picture, the one that says a neutron star is exactly what its name suggests: a star made mostly of neutrons. At first glance, that might sound disappointingly simple, as though after peeling back all the layers of mystery, the answer were just more of the same. But simplicity at such scales is deceptive, because even a world made only of neutrons is hardly ordinary. On Earth, neutrons are elusive. They hide inside atomic nuclei bound with protons, and when freed they decay in minutes. They are not stable companions in our daily chemistry. In the core of a neutron star, however, the density is so high that neutrons become stable, crammed together under pressure so immense that decay is suppressed. It is as if a crowd of restless wanderers suddenly sat down and agreed to stay forever, locked into place by the weight of the cosmos itself. The presence of a few protons in this neutron ocean matters more than one might expect. Protons, positively charged, provide pathways for the star's electrons, which flit among them to maintain balance. Without the protons, the matter would be too stiff, the equations too unyielding. With them, the mixture becomes flexible enough to accommodate the densities present. Imagine a recipe that seems to be all flour but still requires a pinch of salt to taste right. The protons are the seasoning that keeps the neutron stew balanced. Leptons add their own quiet flavour. Electrons move through the dense interior, ensuring that electric charges remain neutral, while neutrinos, though often free to escape once the star has cooled, linger in the early stages of a neutron star's life, carrying away energy, thinning the heat, and helping the star settle into its long, cold existence. They are like fleeting guests at the opening of a play, rushing out after the first act but leaving their influence on the performance that follows. To picture this nucleonic core, one must stretch imagination toward densities that leave ordinary metaphors trembling. Think again of atoms as we know them, vast open spaces, with nuclei like dust motes at the centre and electrons buzzing far away. In a neutron star, that architecture is gone. The space is squeezed out. Nuclei have merged, atoms have collapsed, and what remains is a sea of neutrons, with protons scattered like buoys and electrons darting among them like fish in a crowded tide pool. It is matter without gaps, a cathedral without aisles, every space filled, every seat occupied. This picture of the familiar core has its appeal because it requires no new physics, no untested assumptions. It asks only that we take what we know, neutrons, protons, electrons, and extend it to the limit. The same strong nuclear force that binds protons and neutrons together in ordinary nuclei continues its work, only now across oceans of particles. The same quantum rules that prevent particles from sharing identical states provide the pressure that holds up the star. It is a story of known principles carried into unknown extremes, like a song we recognise played on an instrument almost too large to imagine. And yet, even in this simplest model, the behaviour of matter is not something we can test easily on Earth. Laboratories can smash heavy ions together at high energies, momentarily recreating densities similar to those in neutron stars, but the conditions are fleeting, lasting only trillionths of a second. In the star, the matter endures for millions or billions of years. The difference is like comparing a lightning flash to a steady flame. Both are fire, but their rhythms are utterly different. For those who prefer cautious answers, the the familiar core remains the most attractive. It avoids the complications of quark deconfinement or strange baryons. It suggests that the universe is already strange enough without layering on further speculations, and indeed the measurements of mass and radius from instruments like NICER are often consistent with models that assume largely nucleonic matter, provided the nuclear interactions are described carefully. But there is also a humility in this view. Even if the core is made only of neutrons and protons, it is still a regime of physics beyond our direct grasp. The forces between nucleons at such densities are uncertain. The stiffness of the equation of state depends on details we cannot pin down in terrestrial experiments. So the familiar core is not a dismissal of mystery, but a recognition that sometimes the known can be stretched into realms that feel unknown all over again. To rest in this image for a moment is to feel a kind of calm. Inside the neutron star, perhaps there is no exotic menagerie of particles, no new states of matter with fanciful names, no hidden quark soups or condensates. Perhaps there is simply the same matter we have always known, rearranged by gravity, pressed to its utmost, made stable only by its sheer density. Familiar, yes, but extraordinary all the same. As we close this chapter, picture that city-sized sphere once more, its surface glowing faintly, its crust humming with rivers of superfluid, and beneath it all, in the depths, a core of neutrons resting in their endless crowd. It is ordinary matter rewritten, protons and electrons tucked among them like punctuation marks in a crowded page, neutrinos passing briefly through. It is familiar, but only in the way a mountain is familiar to the stone it is built from. The same material, but on a scale that transforms it entirely. If the simplest vision of a neutron star's core is a crowded ocean of neutrons with a few protons and electrons woven through, then the next step in imagination is to ask whether the crowd might admit stranger guests, particles that on Earth appear only fleetingly in high-energy collisions or inside unstable nuclei, but which might settle in more comfortably under the crushing gravity of a collapsed star. These guests are called hyperons and mesons, names that sound almost like characters in a myth or a play, but in truth they are families of particles, cousins of protons and neutrons, appearing when the densities are so extreme that the boundaries of ordinary nuclear matter blur. Hyperons are baryons, meaning they belong to the same family as protons and neutrons, but with a twist. They carry within them one or more strange quarks instead of the up and down quarks that make up the familiar building blocks of ordinary matter. On Earth, hyperons are not permanent residents. They appear briefly in particle accelerators or nuclear reactions, only to decay almost instantly into lighter particles. Yet in a neutron star, where densities climb beyond nuclear saturation, it is possible that neutrons, so tightly packed, may find it energetically favourable to transform into hyperons. It is as though, in a city so overcrowded that apartments have been filled beyond capacity, residents begin altering themselves just to fit, adopting new identities because the old ones are too cramped. If hyperons arrive, they change the game. Being heavier, they tend to soften the matter, reducing the pressure for a given density. This softening is problematic because if too many hyperons appear, the star may collapse under its own weight, shrinking more than observations allow. In our metaphors, it is like rearranging furniture in an already tight room, and finding that, while the pieces may fit more neatly, the floor begins to sag under the combined load. Some models predict that hyperons should emerge at only a few times nuclear density, but the existence of very massive neutron stars, over 2 solar masses, seems to push back against this, suggesting that either hyperons appear later than expected, or that their interactions provide more stiffness than once thought. Alongside hyperons are another possibility: meson condensates. Mesons are particles made of a quark and an antiquark bound together, and while they are usually ephemeral, under the right conditions they may condense into collective states within dense matter. Physicists have imagined that pions or kaons, specific types of mesons, could form condensates inside neutron stars, aligning into shared patterns like dancers in a hall, moving in perfect synchrony. Such condensates would again soften the matter, lowering the pressure and altering the equation of state. In some theories, they could even alter the way neutrinos move through the star, changing how it cools across millions of years. These ideas might sound speculative, and in truth they are, but speculation here is not the same as fantasy. The densities inside neutron stars are beyond what we can probe directly, so scientists build models, guided by both theory and the clues we gain from observations. Hyperons and meson condensates are not invented from thin air. They are real particles, observed in laboratories, simply placed into the environment of a neutron star where their behaviour might shift. It is as if we are taking known characters from one story and imagining how they would act in an entirely different play, one with unfamiliar rules and settings. To hold this idea gently, you might think of a living room filled with too much furniture. At first, it contains only chairs and tables, the protons and neutrons. But as more guests arrive, the furniture is pushed against the walls, rearranged, and perhaps new. Stranger pieces are brought in. A fainting couch in the corner, a tall cabinet where once there was none. The room is still a room, still serves the purpose of holding people, but its arrangement is transformed. In the neutron star, gravity is the decorator relentlessly pushing, and the hyperons and mesons are the unexpected furnishings reshaping the space. The challenge, of course, is that we cannot step inside the room to see directly. We infer its contents from the outside, from the way the star's mass and radius align, from the way gravitational waves ripple when two neutron stars merge, from the cooling curves traced by their fading light. If the star is too soft, it shrinks, and if it shrinks too much, it contradicts what we have measured. Hyperons and meson condensates therefore walk a narrow line. Possible, perhaps even likely, but constrained by the stiff resistance we observe in the most massive stars. And yet there is a kind of beauty in this possibility. It suggests that the universe may not always choose the simplest path. Instead of cores made solely of neutrons, there may be layers enriched by stranger cousins, particles with unusual quark compositions, or condensates that act collectively, rewriting the script of matter. It is a reminder that when the universe pushes matter to its limits, it often invents new forms rather than surrendering. As you rest with this thought, picture the neutron star again. Beneath the crust, beneath the pasta layers and the superfluid rivers, lies a core where the furniture of matter is rearranged. Some of it remains familiar: neutrons, protons, electrons. But there may also be faint outlines of hyperons, heavy and strange, and condensates of mesons, forming like mist drifting through the dense interior. Whether or not they truly exist there, the very act of imagining them stretches our understanding, inviting us to see matter as flexible, inventive, and surprisingly willing to rewrite itself when pressed beyond the imaginable. There is a moment when you push an idea far enough that the ordinary scaffolding gives way and reveals a more fundamental layer beneath. For matter, that scaffolding is the nucleon, the protons and neutrons that form the core of every atom, the building blocks of nuclei, the bricks of the material world. But physics tells us that even these are not indivisible. Protons and neutrons themselves are made of smaller particles called quarks, bound together by the strong nuclear force, carried by gluons that act like invisible threads tying them tightly into place. On Earth, quarks are never seen alone. They're always confined within nucleons, their bonds so strong that it would take more energy to separate them than to simply create new pairs. But in the extreme conditions of a neutron star core, where density and pressure reach unimaginable scales, scientists wonder, might those bonds finally give way? Might the protons and neutrons dissolve into a soup of their constituents, a sea of free quarks flowing where once there were only nucleons? This idea, known as quark deconfinement, is both startling and oddly logical. If you squeeze matter hard enough, there comes a point where the old structures no longer hold. Atoms give way to nuclei. Nuclei dissolve into neutrons, and neutrons themselves may dissolve into quarks. Each step removes a layer of organisation, leaving something more fundamental, less structured, but still bound by the laws of physics. To picture this, you might think of crushing a loaf of bread. At first it resists, then the slices crumble, then the crumbs themselves are ground to dust, until eventually all that remains is flour, the base ingredient. In the same way, quark matter would be the flour of the cosmos, the fundamental particles stripped of their higher structures, free to swirl together in an unfamiliar state. But if this quark soup exists, it would not be chaotic or meaningless. Quarks come in different types, or flavours, such as up, down and strange, and they also carry a property physicists call colour, not colours like red or green in the everyday sense, but quantum labels that ensure quarks always combine in balanced sets. In a neutron star core, if deconfinement occurs, these colours may organise in extraordinary ways. One of the most intriguing possibilities is that quarks could pair up much like electrons do in superconductors. On Earth, when electrons form pairs in certain materials at low temperatures, they move without resistance, creating superconductivity. In a neutron star, quarks might do the same under immense pressure, forming pairs that allow matter to flow without viscosity. This is called colour superconductivity, a phrase that sounds like a poetic invention, but is in fact a serious branch of theoretical physics. To hold this image gently, think of a ballroom filled with dancers. At first everyone moves individually, jostling for space, occasionally bumping into one another. Then suddenly the music shifts and they pair off, moving in perfect synchrony. The chaos subsides into a coordinated dance, fluid and elegant. That is the dream of colour superconductivity. Quarks, once individual, pairing off into patterns that make the whole system smoother, more stable, more efficient. The colours they carry ensure that the dance is balanced, every step matching another, every move in harmony. If such a state exists, it could dramatically change the properties of neutron stars. Colour superconductivity would alter the star's stiffness, its ability to resist collapse, and could influence how it cools, how it spins down, even how it vibrates when struck by quakes or collisions. It would be a hidden conductor, shaping the symphony from within, invisible to our eyes but present in the signals that eventually reach us. And yet, for all its elegance, the idea remains uncertain. No laboratory on Earth can reach the exact conditions of a neutron star core, the precise combination of high density and relatively low temperature where quark matter might appear. Particle accelerators like the Large Hadron Collider or RHIC can create quark gluon plasma, a state of deconfined quarks, but only at extreme temperatures, billions of degrees, closer to the conditions of the early universe than those inside neutron stars. In the stars, the matter is cold by comparison, dense but not fiery, and the behaviour of quarks in that regime remains mysterious. We peer through equations, through lattice models and simulations, but the truth lies hidden in the cores of stars too distant to touch. Still, there is something dreamlike about this possibility. To imagine quarks, the tiniest building blocks, slipping their bonds and flowing together in rivers of colour, pairing into superconducting states, is to imagine the universe reinventing itself under pressure. It suggests that matter is not static, not fixed to its forms, but always capable of new arrangements when the conditions demand it. And if you pause, you might realise that this progression, atoms to nuclei, nuclei to neutrons, neutrons to quarks, is not only a physical sequence but also a metaphor for how knowledge itself deepens. Each time we think we have reached the bottom, the indivisible, we discover another layer beneath. The atom was once thought to be unbreakable, then it yielded to protons and neutrons, then they yielded to quarks. Perhaps even quarks themselves are not final, but stepping stones to something deeper still. neutron stars in their silent cores may hold the next chapter of that story. So as we sit here in the quiet of night, imagining these collapsed suns, picture not only the dense crowds of neutrons, not only the heavy guests of hyperons and mesons, but also the possibility that all those forms dissolve, leaving a fluid of quarks, colours swirling, pairs forming, a cosmic dance floor hidden inside a star. It is speculative, yes, but it is speculation rooted in physics, in patterns we have already glimpsed on Earth, now extended into the heart of the most extreme objects we know. And if you find the thought too strange, too abstract, let it drift as an image instead. A star, small and dense, filled with a silent ocean of quarks, each one glowing with a colour we cannot see, each one moving in harmony with the others, the whole star humming with a music we cannot yet hear, but which one day, through careful listening, we might begin to understand. If the possibility of quarks dissolving into a fluid of colours seems already extraordinary, then stepping further into speculation leads us to ideas that feel almost like science fiction, though they are pursued with the same seriousness as any other branch of astrophysics. For while neutron stars are already exotic enough in their density and their structure, they may also serve as containers for things we do not yet fully understand. Dark matter, for example, or states of matter so delicately coordinated that they behave less like particles and more like waves of a single, unified being. Dark matter, that elusive substance whose presence is felt in the rotation of galaxies and the scaffolding of the cosmos, has never been directly seen on Earth, never captured in a detector, never held in a hand, and yet its gravitational pull is undeniable, shaping the orbits of stars, bending light, forming the invisible skeleton on which galaxies are built. If dark matter is real, and all evidence suggests it is, then where better to search for its influence than in the densest stars in the universe? Neutron stars, with their immense gravity and compactness, could act like nets, trapping dark matter particles as they pass through. Over millions of years, a neutron star could gather a hidden admixture of dark matter inside its core, altering the way it resists collapse. To picture this, imagine a cake baked with a hidden ingredient. From the outside it looks the same, round and ordinary, but when you slice it open, the texture is different, the flavour subtly changed. A neutron star with a touch of dark matter inside would still appear as a neutron star, but its mass-radius relationship, its stiffness, its cooling behaviour, might carry traces of that hidden filling. If dark matter particles can clump or interact with neutrons, they might stiffen the equation of state, making the star larger than expected for its mass, or perhaps soften it, leading to collapse sooner than we thought. The puzzle of stiffness and softness may not only be about neutrons and quarks, but also about unseen guests sharing the star's hidden heart. Equally dreamlike is the idea of Bose-Einstein condensates forming within neutron star cores. On Earth, Bose-Einstein condensates are created in laboratories by cooling atoms to fractions of a degree above absolute zero, at which point they stop behaving as individuals and merge into a single quantum state, like a chorus singing with one voice. In the star, the environment is not cold but crushingly dense, and theorists have suggested that under these pressures certain bosons, particles with integer spins such as pions or kaons, might condense into collective states. Instead of acting like individual particles, they would flow together as one, their identities blurred, their behaviour unified. The metaphor often used is an orchestra. Normally matter behaves like a crowd at a busy market, each voice calling separately, clashing, overlapping, forming a chaos of sound. In a Bose-Einstein condensate, all those voices merge into a single tone, resonant and pure, as if every instrument in the orchestra chose to play the same note in perfect synchrony. If such a state forms inside a neutron star, it could change everything. The pressure, the stiffness, the way neutrinos escape, even the fate of the star near the Tolman Oppenheimer Volkoff limit. It is, in many ways, one of the most poetic possibilities physics offers, matter not resisting collapse as a cacophony, but instead joining together in harmony, a collective hum at the heart of a collapsed sun. And yet, as with dark matter, the challenge is that these ideas remain beyond direct proof. We can only infer from the stars we observe, from their masses, their radii, their cooling curves, their glitches, their mergers. A neutron star that seems unexpectedly large for its mass might be hinting at dark matter stiffening its interior. A star that cools unusually quickly might be hinting at meson condensates, or Bose-Einstein states altering its neutrino flows. Each clue is indirect, like listening to muffled footsteps behind a door and trying to guess the identity of the visitor. Still, these speculations serve a purpose beyond curiosity. They remind us that neutron stars are not only laboratories of known physics pushed to extremes, but also potential crucibles where unknown physics may reveal itself. If dark matter leaves no trace in earthbound detectors, perhaps it does in the behaviour of stars. If Bose-Einstein condensates are rare on Earth, fragile in our laboratories, perhaps they are robust and enduring in the pressure-cooked interiors of neutron stars. The stars become more than remnants. They become experiments conducted by nature, their results recorded in pulses of light and waves of space-time. As you let this sink in, you might picture a neutron star not as a solid block of neutrons, nor as a soup of quarks, but as something stranger, a sphere with a dark heart, seeded with particles that belong to the hidden majority of the universe, or humming with a chorus of bosons moving in unison, like a song trapped within matter. These images may be speculative, but they are no less compelling for that. They show us that the boundary between science and imagination is not a wall, but a bridge, one we must walk carefully, guided by evidence but sustained by wonder. And in the end, whether dark matter admixtures or Bose-Einstein stars truly exist, the act of considering them stretches our thought. It invites us to look at the night sky not only with the eyes of what we know, but also with the openness of what might be. For the neutron star, compact and silent though it is, may be more than just the sum of neutrons. It may be a vault for secrets we have not yet learned to unlock. Every structure in the universe, no matter how extraordinary, has a limit. Bridges can only carry so much weight before the cables strain and snap. Balloons can only hold so much air before the skin stretches and bursts. Even mountains, though they seem eternal, eventually crumble under the endless wear of water and wind. Neutron stars, for all their unimaginable density and resilience, are no different. They too have a breaking point, a wall that gravity erects in silence, and it is called the Tolman Oppenheimer Volkoff limit, or simply the TOV limit. To understand this limit, imagine once more the balance that defines a neutron star. On one side, gravity pulls inward with overwhelming force, trying to compress the star smaller and smaller. On the other side, the quantum rules of neutrons resist, pushing back, their degeneracy pressure acting as a kind of invisible scaffolding. For most neutron stars, this balance holds, precarious yet steady. But as the mass grows larger, perhaps because the original star was unusually massive, or because the neutron star gathers more material from a companion, the scaffolding begins to tremble. There is only so much resistance neutrons can offer before the weight becomes too great. The calculations of Richard Tolman, J. Robert Oppenheimer and George Volkoff in the 1930s revealed this invisible cliff. They show that beyond a certain mass, roughly 2 to 3 times that of the Sun, no equation of state could save the star. The pressure of neutrons would no longer be enough, the scaffolding would fold and the collapse would continue without end. Beyond the TOV limit, the neutron star has no choice but to become something else, a black hole. To hold this idea gently, think of a rope pulled taut between 2 climbers. At first it stretches but holds, its fibres aligned, its strength intact. As the weight increases, the rope groans, fibres snapping one by one until at last the whole line gives way. The TOV limit is that final moment for neutron stars, the point where no matter how the fibres are arranged, whether the core contains neutrons, hyperons, quarks, or condensates, gravity demands more than physics can provide. The rope snaps, and the star falls into darkness. We do not know the exact value of the TOV limit, because it depends on the details of the equation of state, the stiffness or softness of matter at the highest densities. Observations suggest it lies somewhere around 2.0 to 2.3 solar masses for non-rotating stars, though rapidly spinning stars can hold slightly more, their centrifugal force giving them a little extra support, like a dancer spinning out her arms to resist a fall. But even spin cannot postpone collapse forever. The tightrope is too narrow, and eventually the weight wins. Astronomers look for clues of the TOV wall in the cosmos. When two neutron stars collide, as they did in the famous event GW 170817, the result may be a hypermassive neutron star, supported for a brief time by spin and thermal pressure, but within seconds or minutes it collapses into a black hole. The timing of that collapse, measured in the fading signals of gravitational waves and gamma rays, gives us precious information about where the TOV limit lies. Each merger becomes not only a spectacular cosmic event, but also a test of the wall's location, as though the universe itself were conducting experiments in limits and sending us the results in ripples of space-time. To picture the TOV limit is to recognise the fragility hidden inside grandeur. A neutron star may weigh more than the Sun, may spin hundreds of times per second, may fling beams of radiation across light years with the precision of a clock, but if its mass crosses that invisible boundary, it has no recourse. It falls, silently, inexorably, into the state we call a black hole. The very properties that made it stable, the degeneracy pressure, the nuclear forces, are overwhelmed. Beyond the wall, resistance vanishes, and gravity holds the final word. There is something humbling in this, and something familiar too. We often imagine limits as abstract, distant things, yet in truth we live with them daily. A shelf holds until the books are too many. A heart beats until it tires. A mind stretches until it needs rest. The TOV limit is the cosmic echo of these truths, written not in wood or flesh, but in neutrons and space-time. It reminds us that even the strongest balance has its threshold, and yet to think of it not as an end but as a threshold changes its meaning. The collapse into a black hole is not a failure but a transformation. The rope may snap, but what comes after is not nothing. It is something new, darker, stranger, a horizon from which light itself cannot escape. The neutron star reaches its limit and hands the stage to another actor in the cosmic play. So when we speak of the TOV wall, we are not only speaking of numbers on a page or masses measured in solar units. We are speaking of a profound boundary in nature, a line beyond which one kind of existence ceases and another begins. It is a reminder that stars like us live within the laws of balance, and when those laws can no longer be satisfied, they change form. As we move forward, we will see how collisions of neutron stars probe this wall, how gravitational waves and flashes of light help us trace its outline. For now, let us rest with the image of a star standing at the edge of gravity's demand, a rope stretched, a balance trembling, the weight of the cosmos pressing down. The TOV limit is the line where matter's courage ends and gravity takes over, the place where the story of neutron stars yields to the story of black holes. There are few events in the universe as dramatic as the meeting of two neutron stars. For billions of years they may orbit one another in silence, bound by gravity, spiraling slowly closer as they radiate energy away in faint ripples of space-time. Their dance is long and patient, a courtship measured not in days or years but in cosmic epochs. And then, at last, the distance closes, the spiral quickens, and in the final seconds their orbits blur into a frantic whirl before the two stars collide in a flash of energy that lights up the cosmos. For us, On Earth, the most famous of these encounters was seen in 2017, when observatories detected both gravitational waves and light from the merger of two neutron stars in a galaxy 130 million light-years away. The event was labelled GW 170817, a name that to astronomers marks its date of discovery, but to the wider world it marked something more profound. The first time humanity witnessed a cosmic collision with two senses at once, not only hearing the faint vibrations of space-time, but also seeing the light that followed. It was a moment when the universe seemed to lean close and whisper, "This is how my secrets are revealed." The gravitational waves arrived first. Instruments like LIGO and Virgo recorded the faint stretching and squeezing of space-time as the two stars spiraled together, each orbit sending another ripple outward. The signal grew stronger and higher in pitch as the stars closed the gap, much like the rising tone of a violin string tightened before it snaps. In those ripples lay information about the stars themselves, not only their masses, but also how easily they deformed under each other's gravity. A stiffer star, resisting distortion, produces one pattern. Softer star, yielding more, produces another. This property is called tidal deformability, and it is a key to unlocking the stiffness or softness of the equation of state. In the delicate wiggles of space-time, scientists could read the resilience of matter itself. Then came the light. Just seconds after the gravitational waves passed, satellites detected a short burst of gamma rays, the high-energy flash that marks the final collision. Hours later, telescopes around the world turned to the patch of sky where the event had occurred and saw the afterglow, a kilonova, an explosion bright with heavy elements, glowing in colours that shifted as it cooled. Gold, platinum and other precious metals were forged in that fire, scattered into space, ready one day to seed planets, jewellery and circuitry. It is humbling to realise that the rings on our fingers and the circuits in our devices may be the children of ancient neutron star collisions. The orchestra of signals did not stop there. Radio telescopes listened for the expanding shockwave. Infrared observatories watched the cooling embers. Across the spectrum, the universe provided instruments, each adding its own line of music to the symphony of the merger. Multi-messenger astronomy, as it is now called, became not just a phrase but a lived reality. Gravitational waves as percussion, gamma rays as the brass, optical light as the strings, radio as the woodwinds, all blending into a single performance that revealed more than any single instrument alone could play. For scientists, the significance was immense. The tidal deformability measured from GW 170817 narrowed the possibilities for the neutron star equation of state, pruning away models that were too soft or too stiff. The timing of the gamma ray burst provided insight into whether a hypermassive neutron star briefly survived before collapsing into a black hole. The kilonova gave direct evidence of heavy element creation. Each piece added a brushstroke to the portrait, a portrait painted not by hands but by signals arriving from 130 million years in the past. To hold this gently in your thoughts, imagine two stones dropped into a pond far away. The ripples expand outward until, after travelling across unimaginable distances, they finally touch the edge of your shore. At the same time, you see a flash on the horizon, faint but unmistakable. From those ripples and that flash, you reconstruct the entire story of the stones, their weight, their speed, the shape of their splash. That is what astronomers did with GW 170817, only their pond was the fabric of space-time, and their ripples were caught by detectors cooled and tuned to a sensitivity so precise they could measure distortion smaller than a fraction of a proton's width. And as wondrous as that one event was, it is only the beginning. More neutron star mergers have since been observed, each adding its own variations, each refining our understanding of matter under extreme pressure. The orchestra continues, sometimes faint, sometimes clear, but always carrying in its music the voice of matter at the edge of what physics allows. There is a deep comfort in this too. Collisions that from one perspective are catastrophic, the destruction of stars, the release of energies beyond comprehension, are also creative, giving birth to elements, to knowledge, to new chapters in the cosmic story. The violence of the merger becomes the quiet enrichment of the universe, scattering gold and platinum, scattering data and insights, scattering light that reaches us across epochs to be turned into understanding. So when we speak of collisions that shake space-time, we are not speaking only of violent ends. We are speaking of revelations, of the universe playing its instruments in a register we are just now learning to hear. Each merger is a performance written not for us but available to us, a song of gravity and light carried across the ages, reminding us that even in destruction there is creation, and even in chaos there is meaning. When two neutron stars merge, or when a neutron star gathers too much mass from a companion, there are moments when the object that forms is balanced on the thinnest of edges. It is heavier than any neutron star has a right to be, so close to the Tolman Oppenheimer Volkoff limit that collapse seems inevitable, and yet, for a while, it resists. This is the realm of narrow survivals, where stars walk a cosmic tightrope, their continued existence measured not in millennia, but sometimes in seconds, minutes, or hours, supported by fleeting forces that eventually yield to gravity's unrelenting demand. One of the most important of these temporary supports is rotation. When a star spins, centrifugal force pushes outward, countering gravity's pull, and the faster the spin, the greater the effect. For a neutron star spinning hundreds of times per second, this support can make the difference between immediate collapse and brief survival. Imagine a potter's wheel spinning clay. The rotation flings the clay outward, flattening it, holding it wider than it would otherwise be. In a similar way, the rapid spin of a neutron star can distribute its mass, letting it remain stable just a little longer than gravity would otherwise allow. There is, however, a price to this balance. The star cannot spin forever. Magnetic fields, radiation, and gravitational waves slowly sap its energy, slowing the rotation. The outward push weakens, the balance tilts, and sooner or later, the star must face its fate. For some, the slowdown leads to collapse into a black hole. For others, it may mean settling into stability at a smaller mass, if enough material is shed in the process. Either way, the narrow survival is temporary, a borrowed reprieve that cannot last. In the aftermath of mergers like GW 170817, astronomers think a hypermassive neutron star sometimes forms, a star that exceeds the TOV limit, but is held up by both rapid rotation and by the extra heat generated in the collision. Thermal pressure, like steam in a kettle, briefly adds support, but as the star radiates energy away, cooling and spinning down, its borrowed strength fades. Within seconds to minutes, the hypermassive star collapses, vanishing behind the horizon of a new black hole. The signals we receive, the gravitational waves, the gamma-ray bursts, the fading kilonova, are shaped by this fleeting balance, telling us how long the star managed to walk the tightrope before falling. The concept of narrow survival also opens the door to speculation about alternative fates. Some theorists suggest that under the right conditions, instead of collapsing directly to a black hole, a star could settle into a more exotic form such as a quark star. In this scenario, the collapse squeezes neutrons into quarks, but instead of continuing without end, the matter finds a new stability, a different plateau on the landscape of physics. These quark stars, if they exist, would be rare, perhaps transient, but they would embody the idea that collapse does not always mean finality. It can mean transformation, a new kind of balance born in extremity. To picture these stars as tightrope walkers is not only metaphorical but also revealing. Balance here is delicate, precarious, and temporary. The rope is stretched thin, gravity yawns below, and the star teeters with every step. For a time, the spin is the balancing pole, the thermal pressure the quickened breath, the stiffness of matter, the tension in muscles. But all of these supports fade. The pole grows heavy, the breath slows, the muscles tire, and at last the walker stumbles. The fall is not a failure but an inevitability, written into the laws of physics, and the rope is only ever meant to be crossed once. And yet, even in these narrow survivals there is beauty. The signals they produce, the ripples in space-time, the flashes of light, the patterns of matter flung into space, become beacons of knowledge. They allow us to measure the stiffness of the equation of state, to constrain the TOV limit, to glimpse the possibilities of quark matter or other exotic states. In a sense, the star's struggle to hold on becomes our opportunity to learn. Its brief dance on the edge, a message written in the sky. From the perspective of time, these survivals are brief, but to us they feel profound. A hypermassive neutron star that lives for just a second or two before collapsing has already outlived our ability to imagine its conditions. In that 1 second, it contains densities, fields, and forces beyond anything we can replicate on Earth. A natural laboratory conducting an experiment for us, and then recording the results in the universe's memory. When we detect its signals, we are reading those notes long after the experiment is complete. So as we rest in this thought, imagine again the tightrope. A narrow line suspended above an abyss, a star walking with impossible poise, sustained by spin, by heat, by forces that cannot last. It may stumble into a black hole, or perhaps into a new state of matter, but for a brief and shining moment, it survives against all odds. Its balance is not permanent, but its message is enduring. Even at the edge of collapse, even in narrow survivals, the universe has more to teach us, and more ways to astonish us with the elegance of its extremes. When we think of neutron stars, we often imagine heat, birth in a supernova, temperatures in the millions of degrees, X-rays streaming from magnetic hotspots, and indeed, when they are young, they glow with the leftover fire of collapse, radiating energy into space, cooling steadily over thousands and then millions of years. But the story of their cooling is more than a detail. It is a test, a verdict, a way for the universe to judge which theories of matter are allowed and which must be discarded. In 2024, astronomers studying some of the coldest neutron stars ever observed found themselves confronted with verdicts that were sharper and more decisive than they had expected. These stars, silent and faint, became harsh judges of our models, pruning away almost 3/4 of the possibilities we had imagined for the equation of state. To understand why, we must first linger on how a neutron star cools. At its birth, it is a furnace of trapped neutrinos, still shedding the heat of collapse. Over time, photons stream from its surface, while neutrinos leak from its interior, carrying energy away. The exact rate at which this happens depends on what the star is made of, what particles live in its core, what interactions are possible. If the core is nucleonic, just neutrons and protons, the cooling follows one path. If hyperons or meson condensates are present, neutrinos may carry energy away more efficiently, and the star cools faster. If quark matter fills the heart, the cooling might be faster still. Each possibility leaves a fingerprint in the star's temperature as it ages. Astronomers cannot watch a single neutron star cool from youth to old age. The timescales are too vast. But by observing many stars of different ages, they can build a cooling curve, a rough map of how temperature declines with time. And sometimes, in that map, outliers appear. Stars that are colder than expected for their age, or warmer, their behaviour whispering clues about the processes hidden inside. The 2024 study was just such a whisper, though more like a stern announcement than a quiet hint. Using observations in X-rays and other bands, astronomers identified neutron stars that were unusually cold given their ages. These temperatures could not be reconciled with many of the softer equations of state, nor with models that relied too heavily on exotic particles that would accelerate cooling too quickly. Like a teacher marking out wrong answers on an exam, the data crossed out large swathes of theory, leaving behind only the models that could match the chill. By some estimates, more than 75% of the proposed equations of state were effectively ruled out. To hold this gently in your mind, imagine a room full of clocks, each ticking away with a different rhythm. You cannot see the gears inside, but by listening closely you can tell which are steady, which are fast, which are slow. Now imagine discovering that most of the clocks are running too quickly, their gears slipping, their timing wrong. You set them aside, leaving only the few that keep time correctly. That is what the cold neutron stars did for us. They told us which models of matter kept time with the universe, and which did not. The implications were profound. Some ideas about hyperon-rich cores, long considered plausible, suddenly looked less likely. Some versions of quark matter, particularly those that allowed rapid neutrino cooling, were narrowed or excluded. Even certain nuclear physics assumptions about how neutrons interact at high density had to be rethought. The stars, simply by being colder than expected, had judged our theories and found most of them wanting. There is a stark beauty in this kind of science. No laboratory on Earth could compress matter to these densities for millions of years. No accelerator could maintain the pressure and watch the slow loss of heat. Only the stars themselves can perform such an experiment, and they do so not for us, but simply because that is their nature. We arrive as latecomers, pointing telescopes across light years, and from their faint glimmers we reconstruct the verdicts they have already given. And yet, for all the sharpness of those verdicts, the manner in which they arrive is quiet. A neutron star does not announce its temperature with fanfare. It does not display numbers across its surface like a clock. It glows faintly, in X-rays so soft they can barely be seen, and only through patient measurement, careful subtraction of background light, and long hours of observation can astronomers discern the truth. It is a reminder that the harshest judges can be the quietest, that decisive answers can come in whispers. As you picture this, think of the cold neutron star not as a dead ember, but as a stern teacher, its faint glow like chalk on a board, marking equations with a firm hand. It does not scold, it does not shout, but it removes what is wrong, leaving us with only the right paths forward. And in that way, the coldest stars have become some of the most enlightening, narrowing the maze of possibilities until the way ahead is clearer. The pruning of theories in 2024 was not the end of the story, but a sharpening of it. It showed us that even in their silence, even in their faintness, neutron stars continue to instruct. They are not only reminders of collapse and extremes, but also guides. Their cooling curves maps that point us toward the truth. In the end, they may not only reveal the behaviour of matter at high density, but also illuminate questions about quantum gravity itself, since any unification of physics must pass the test set by these harsh but honest judges. So as we drift into the quiet of this night, hold the image of these cold stars, distant, dim, yet decisive. They sit in the dark, shedding heat into space, their temperatures carrying messages across light years, messages that cross out most of what we thought we knew, and leave us humbled, but also more certain. In their chill there is clarity, and in their faint glow there is guidance. When Einstein first set out the principles of general relativity, he described gravity not as a force, but as the bending of space-time itself, a fabric curved by mass and energy. For more than a century, that theory has been tested, probed, and confirmed in ways that would have astonished its author, from the bending of starlight during eclipses to the ripples of space-time measured in gravitational waves. Yet perhaps the most delicate and relentless of these tests comes not from telescopes watching distant galaxies, or detectors catching faint vibrations, but from a quiet system of 3 stars, tucked away 4,200 light-years from Earth, orbiting one another with a precision so sharp that it feels like a cosmic clockwork, a timepiece wound by gravity itself. At the heart of this system is a neutron star, and around it two white dwarfs. Together they form PSRJ 0337 plus 1715, a laboratory for physics as exacting as any built on Earth. The neutron star in this system is a pulsar, spinning hundreds of times per second, sending beams of radio waves that sweep past us with clock-like regularity. Every pulse is like the tick of a second hand, arriving at Earth so predictably that even the tiniest deviations in timing can be detected. Around it move two white dwarfs, the remnants of stars that once shone but now glow faintly, their fusion long extinguished. One white dwarf orbits the pulsar closely, circling every day and a half, while the other orbits the pair at a greater distance, every 327 days. It is a system that could have been lifted from the imagination of a watchmaker, gears within gears, ticking and turning with mechanical grace. The beauty of this arrangement lies in how it allows us to test gravity's deepest rules. According to general relativity, all objects fall the same way in a gravitational field, regardless of their mass or composition. This principle, called the equivalence principle, has been tested countless times on Earth, from Galileo's imagined experiment dropping stones from the Leaning Tower of Pisa, to lunar astronauts dropping hammers and feathers in the moon's thin airless environment. But never before has it been tested with objects as extreme as neutron stars, with their immense densities and their sensitivity to gravitational curvature. In PSRJ 0337 plus 1715, the outer white dwarf pulls on both the pulsar and the inner white dwarf. If the neutron star fell differently toward the outer companion than the inner, white dwarf did, even by the tiniest fraction. The timing of the pulsar's ticks would reveal it. For years, astronomers have listened to those ticks, gathering data, and so far the result is striking. The neutron star and the white dwarf fall together, locked in step as if choreographed. No deviation has been found, no crack in Einstein's principle. Even here, under the most extreme conditions, general relativity holds. To hold this gently in your imagination, think of three dancers bound by invisible strings. The smallest twirls quickly, the largest circles slowly, and yet their motions are locked together, their steps perfectly coordinated. Watch closely, and you might expect to see a stumble, a misstep, a slight drift in timing. But no, the dance continues, precise, flawless, every movement in rhythm. That is the triple system, its choreography dictated by gravity, its rhythm measured by the steady tick of the pulsar. For scientists hoping to find cracks in general relativity, this is both humbling and frustrating. The neutron star, with its immense density, its strong field gravity, and its potential for exotic interiors, seemed like the perfect place for new physics to appear. If any object could reveal where Einstein's theory falters, it would be a neutron star. And yet, PSRJ 0337 plus 1715 has so far offered no such cracks. The timing of its pulses confirms Einstein's watch is still running, steady and true. But this too is beautiful in its own way. It tells us that the scaffolding of relativity extends further than we might have dared to expect, that even when matter is compressed to densities beyond atomic nuclei, even when space and time are bent around a pulsar spinning hundreds of times per second, the old equations still trace the path. It is like testing an antique clock under pressure, shaking it, spinning it, pressing it, and still finding the hands circling in perfect time. This does not mean that new physics will never appear. The neutron star core remains hidden, its composition still unknown, and there may yet be conditions, higher densities, greater energies, deeper collapses, where relativity must give way or merge with quantum mechanics. But for now, the lesson of PSRJ 0337 plus 1715 is one of resilience. The old watch still keeps time, and its ticks echo across light years without fail. To reflect on this is to feel a certain comfort. We live in a universe that is, in many ways, unpredictable. Stars explode, matter collapses, galaxies collide. And yet beneath that chaos lies a rhythm so reliable that a pulsar's beat can be trusted more than the clocks on our walls. Even when surrounded by companions, even when pulled by multiple gravities, the pulsar's signals arrive, unwavering, a heartbeat from across the cosmos. So let us sit with this thought. In a quiet corner of the Milky Way, a neutron star and two white dwarfs orbit one another in an endless dance. Their timing is flawless, their motion unbroken, their signals a steady metronome for physics itself. Einstein's watch still runs, and for now the universe keeps its appointments exactly as predicted. The mystery of the neutron star's core remains, but the rules of falling, of orbits, of space-time itself stand firm. The watchmaker, it seems, still knows the time. For most of history, the heart of a neutron star was a place left entirely to imagination. No laboratory could hope to reproduce its pressures, no forge could compress matter to its density, no equation could capture its complexity without wandering into uncertainty. And yet, in the last few decades, humanity has built machines that reach further into that mystery than anything before. They are not the size of cities, but of landscapes. Particle accelerators like the relativistic heavy ion collider at Brookhaven in New York, or the Large Hadron Collider under the farmland of Switzerland and France. In these rings of steel and magnets, heavy nuclei are smashed together at near light speed, creating for a fraction of a second tiny droplets of matter that may echo the conditions inside neutron stars. These collisions are brief, so brief that the timescales make lightning look eternal. They last only trillionths of a second, and yet in that instant the temperature rises to trillions of degrees, the density surges, and the quarks inside protons and neutrons are shaken free. What emerges is called quark-gluon plasma, a state of matter in which quarks and gluons roam unbound, no longer confined within nucleons. It is sometimes described as the primordial soup, the form of matter that filled the universe in the first microseconds after the Big Bang, before it cooled enough to condense into the particles that now form stars and planets. To hold this image, imagine dropping stones into a still pond, but instead of ripples, what emerges are splashes so violent they briefly boil the water, rearranging its very structure. The accelerators create these splashes in the vacuum, droplets so hot and dense they cannot last, but they are glimpses of matter in its most fundamental state. Physicists peer into them with detectors the size of cathedrals, watching the fragments of particles spray outward, reconstructing from the debris the brief story of what happened at the heart of the collision. And while these plasmas are far hotter than neutron stars, the stars are dense but relatively cool compared to these experiments, they still provide vital clues. They tell us how quarks interact when freed, how gluons bind them, how matter behaves when pushed beyond the boundaries of nuclei. By combining these insights with astrophysical observations, scientists narrow the possible equations of state. The laboratory and the cosmos meet, one in a controlled burst beneath the ground, the other in the silent heart of a collapsed star, both speaking the same language of matter under strain. There is something humbling about this parallel. On Earth, we spend billions of dollars, years of planning, armies of engineers to smash atoms together and catch the briefest glimpses of exotic matter. In space, neutron stars do it effortlessly, sustaining those conditions for millions of years, not in fleeting sparks, but in enduring stability. It is as if the universe is saying, I have already run these experiments for you. All you need to do is watch carefully. The accelerators are our attempt to catch up, to build tiny, fleeting echoes of what nature performs daily at cosmic scale. The link between colliders and neutron stars also carries a poetic symmetry. The quark-gluon plasma made in laboratories is thought to resemble the matter of the early universe, before it cooled into protons and neutrons. Neutron stars may represent the reverse journey. Ordinary matter compressed so tightly that it reverts to something like its primordial state. One is the echo of the beginning, the other may be a glimpse of an ending, or at least of a stage that follows collapse. Together they form a circle, reminding us that the strange states of matter are not new inventions, but part of the universe's long memory. It is easy, when reading of colliders, to think only of scale, the vast magnets, the underground tunnels, the detectors towering above scientists. But at their heart, these experiments are fragile, delicate things. The droplets they create are so small and fleeting that they cannot be touched directly, only inferred from the patterns of particles that scatter outward. It is not unlike trying to learn the shape of a vase by listening to the sound it makes when shattered. Neutron stars, by contrast, are entire galleries of vases, intact and enduring, waiting patiently for us to tune our instruments and read their signals. And yet, the two approaches are not rivals but partners. Without the colliders, we would not understand the physics of quarks and gluons well enough to build models of neutron stars. Without the neutron stars, we would not know whether those models hold true at scales unreachable on Earth. The accelerators provide the first notes, the stars the full symphony. Together, they tell us how matter behaves when pushed to its breaking point. To rest with this thought is to feel a quiet awe at humanity's ingenuity. We are small creatures on a small planet, yet we have learned to build machines that mimic the universe's most extreme laboratories, if only for the briefest of moments. And by listening to the echoes from neutron stars, we learn that our fragile experiments are not in vain, that they connect to realities vast and enduring. So picture this: deep beneath the Earth, in tunnels humming with magnets, quarks and gluons flash free for a heartbeat, reminding us of the universe's earliest moments. Far above, across light years of space, neutron stars hold their cores steady, perhaps filled with the same free quarks, perhaps not, their pulses carrying news of the state within. Between the two, a dialogue continues, the experiments of humanity and the experiments of nature, both illuminating, both incomplete, but together edging us closer to the truth of matter at the edge of law. Every scientific theory is a lens, a way of looking at the world that brings certain details into focus while leaving others blurred. For more than a century, two lenses have guided us. General relativity, Einstein's vision of gravity as the bending of space-time, and quantum mechanics, the strange but precise rules that govern the behaviour of particles on the smaller scales. Each works beautifully in its own realm. Relativity describes planets, stars, galaxies, and the expanding universe with elegance. Quantum mechanics describes atoms, molecules, and the subatomic world with astonishing accuracy. Yet the two lenses do not fit together. When we try to look through both at once, when matter is both very dense and curved by gravity, and also governed by quantum rules, the view fractures. It is as if one eye is focused on the horizon, while the other stares at the grain of sand beneath our feet. Somewhere, the perspectives must merge, but we have not yet found the way. Neutron stars sit precisely at that crossroads. They are massive enough that their gravity warps space-time intensely, bending light, stretching orbits, curving the fabric around them into steep wells. Yet they are also compact enough that quantum forces matter. Neutrons packed by the Pauli exclusion principle, protons and electrons squeezed together, quarks perhaps freed or paired. They are laboratories not only of dense matter but of the conflict between our greatest theories. In their interiors, general relativity and quantum mechanics are forced to share the stage, and we, the distant audience, are left to wonder how the play unfolds. To hold this gently, imagine a chalkboard filled with equations. On one side, smooth curves and continuous fields describe the bending of space and the flow of time. On the other side, discrete symbols and probability waves describe particles flickering in and out of states. At the centre, the chalk marks overlap, smudging into uncertainty. The neutron star is that chalkboard, scribbled by nature itself, the equations not yet reconciled, the picture unfinished. Each observation we make, of mass, of radius, of cooling, of collisions, is like catching sight of a few more chalk lines, clues to how the two realms may be drawn together. Some physicists believe neutron stars may provide the first real hints of quantum gravity, the long-sought theory that unifies relativity and quantum mechanics. If the stars are heavier than expected, or smaller, or if their cooling follows unusual patterns, those deviations might point toward new physics. Even the way they collapse, whether immediately into black holes or through intermediate states, can test ideas about how space-time behaves when pushed to extremes. They are not black holes yet, not fully beyond our ability to observe, but they stand at the threshold, close enough to reveal the tension, but open enough to let us see inside. The discovery in 2024 of unusually cold neutron stars is an example of this tension. By ruling out so many equations of state, those stars also ruled out some speculative theories of quantum gravity, ideas that had seemed mathematically elegant but failed when tested against nature's verdict. It is a reminder that whatever the true theory is, it must pass the stern examination of these compact stars. They are not indulgent teachers. They accept only the right answers. To make sense of this frontier, consider the image of two maps laid atop each other. One map shows mountains and rivers, the other roads and cities. Each makes sense on its own, but together they overlap awkwardly, their lines mismatched. General relativity is the map of spacetime's mountains and valleys. Quantum mechanics is the map of particles and probabilities. Neutron stars are where the maps must be reconciled, where the mountain roads and river bridges must connect in a coherent whole. If they do not, the maps are incomplete. And yet, there is patience in this puzzle. The stars are not rushing to reveal their secrets. They spin, they cool, they pulse, they merge, following their own rhythms, indifferent to our questions. We must be the ones to listen carefully, to measure with precision, to compare observations with theory. Each gravitational wave, each pulse recorded, each cooling curve is another hint. The final synthesis may not arrive soon, but the hints accumulate, like puzzle pieces slowly forming the outline of a picture. For those who dream of unification, neutron stars are both tantalizing and humbling. They show us where our theories must meet, but they do not hand us the answer. Instead, they whisper contradictions, offer clues, force us to reconsider assumptions. They are both obstacle and guide. And perhaps that is fitting, because the deepest truths are rarely given freely. They must be earned, discovered in patience, wrestled from the silence of the cosmos. So as we sit with this thought tonight, picture a neutron star not only as a collapsed core, but as a boundary stone, standing between the territories of Einstein and the quantum. On one side, space-time bends smoothly. On the other, particles flicker and dance. At the star's centre, the two realms blur. The chalkboard is covered with equations we do not yet know how to reconcile. But in that blur lies possibility, and in that uncertainty lies the promise of a deeper understanding. We have wandered a long way tonight, from the steady rhythms of our sun to the fragile limits of white dwarfs, from the strange pasta shapes in neutron star crusts to the speculative soups of quarks and the dreamlike harmonies of Bose-Einstein condensates. Along the way, we have seen the sun as a model of balance, white dwarfs as reminders of resistance, neutron stars as lighthouses and magnets, and black holes as the shadows that wait beyond every limit. We have walked with hyperons and mesons, danced with quark colours, imagined dark matter slipping silently into stellar cores. We have listened to gravitational waves from collisions, seen colonovae scatter gold across galaxies, watched pulsars tick like clocks, and allowed cold stars to prune away our theories with stern efficiency. And now, as the night deepens, we find ourselves standing at the edge of what is known, gazing into the heart of what remains uncertain. The question of what lies inside a neutron star is not only a curiosity, it is a key, a riddle placed at the meeting point of our greatest theories. If the cores are stiff, resisting compression, then certain exotic states must be rare or absent. If they are soft, yielding easily, then quarks or hyperons or condensates may dwell inside. Each possibility carries consequences, not only for astrophysics, but for the way we understand the fundamental forces of nature. The strong force, the one that binds quarks into nucleons, is still not fully mapped at the densities neutron stars demand. By probing these stars, we're not merely describing dead remnants, but exploring the very rules that shape matter. To hold this in your thoughts, imagine placing your ear against the side of a great mountain. You would expect silent, stone upon stone weight pressing downward, and yet if you listened long enough and carefully enough, you might hear faint vibrations, rock shifting, rivers running deep below, even the tremor of distant quakes. A neutron star is like that mountain, outwardly still, but inside it beats with processes we cannot yet name. The pulses, the gravitational waves, the cooling curves, these are the vibrations we catch, the faint heartbeats of matter at its edge. Cracking the equation of state, as scientists call it, is more than filling in a line on a chart. It is an act of listening, of hearing the mountain's hidden pulse. If we can decode it, we will not only know what neutron stars are made of, but also push closer to a unified description of the universe. We will see where general relativity and quantum mechanics begin to overlap, where nuclear physics shades into cosmology, where matter itself decides how much strain it can endure before yielding to gravity's insistence. There is something profoundly human about this effort. We cannot reach a neutron star, cannot scoop up a fragment, cannot even send a probe near its surface without it being destroyed. And yet we persist, using light and waves as translators, building instruments so delicate they can measure distortions smaller than a proton's width, waiting patiently for rare collisions billions of years in the making. It is an act of faith as much as of science. Faith that the universe speaks a language we can eventually understand. Faith that by listening long enough, carefully enough, we will decipher its rhythm, and still, for all our cleverness, the heart of the star remains hidden. We can weigh them, measure them, listen to their pulses, trace their cooling, catch their mergers, and yet we cannot say with certainty what lies in the very core. It may be neutrons packed impossibly close. It may be strange new states. It may be something we have not yet imagined, a form of matter awaiting discovery. The mystery remains intact, and perhaps that is fitting. For mysteries are not only obstacles, they are invitations, beckoning us forward, asking us to wonder more deeply. As we near the end of our journey tonight, let yourself rest in that space of invitation. Do not rush to answers. Instead, hold the image of a star the size of a city, glowing faintly, spinning steadily, its crust etched with pasta patterns, its interior threaded with superfluid rivers, its core filled with either familiar neutrons or strange and unknown guests. Imagine its pulses arriving at Earth after travelling for millennia, steady ticks of a clock we cannot touch. Imagine gravitational waves spreading outward like ripples from stones thrown long ago, reaching our detectors just as we are learning how to listen. These are the heartbeats of the mountain, the signs that something hidden continues to live and move inside. It is not necessary to know the final answer tonight. It is enough to rest with the questions, to let them drift in your mind as you drift towards sleep. For the stars themselves are patient. They have held their mysteries for millions of years, and they will hold them still while we search. Our role is simply to listen, to wonder, and to walk slowly toward the edge of understanding, where the known fades into the unknown and the unknown beckons us on. And so we arrive at the quiet end of our journey, having walked together through the thresholds of stars and into the hidden chambers of neutron star cores. We began with balance, with the sun holding itself steady against collapse, its neutrinos whispering its inner heat across the void. We saw white dwarfs, embers of stars supported by the crowding of electrons, each seat filled in the cosmic theatre until the auditorium could hold no more. We watched as the Chandrasekhar limit tipped those embers into collapse, leaving behind neutron stars, dense and compact, the size of a city but heavy enough to hold the mass of suns. We traced their surfaces, iron crusts studded with pasta-like patterns. Gnocchi and spaghetti formed not of flour, but of neutrons and protons bent by pressure. We imagined rivers of superfluid neutrons gliding beneath, frictionless, eternal, sometimes tugging on the crust and jolting a pulsar's spin in tiny glitches. We listened to pulsars themselves, spinning faster than thought, beaming signals across space like lighthouses sweeping the cosmic shore. We shivered at the thought of magnetars, their magnetic fields so intense they could erase our memories of steel and stone, their starquakes shaking crusts in flashes brighter than entire galaxies. We measured them too, not with hands or scales, but with light and shadows, with the faint beams caught by NICER on the space station, mapping hotspots as stars rotated, bending light with gravity strong enough to curve it back into our view. We weighed them by the tug on their companions, watching binaries dance and calculating masses from their orbits. We puzzled over their radii, debating stiffness and softness like one might compare cushions, some models yielding too easily, others holding too firmly, the truth perhaps lying somewhere in between. We imagined the cores filled with neutrons, protons and leptons, the familiar picture stretched to extremes. Then we welcomed stranger guests, hyperons with strange quarks, mesons condensing like dancers in perfect synchrony, rearranging the furniture of matter's room. We dissolved nucleons into quarks, poured them into a soup, and wondered if colour superconductivity might pair them into a dance as elegant as any ballroom. We allowed even more speculative guests to enter, dark matter slipping silently into the mix, Bose-Einstein condensates forming orchestras, where every particle plays the same note in harmony. We touched the Tov wall, the boundary where gravity demands surrender, where stars can no longer resist and collapse into black holes. We heard the echoes of mergers like GW170817, ripples in space-time carrying news across 130 million years, gamma-ray flashes lighting the darkness, kilonovae scattering gold and platinum into the galaxy. We saw hypermassive stars walk the tightrope of narrow survivals, spinning themselves into balance for brief moments before falling, their fates written in the choreography of collapse. We listened to cold stars pruning our theories, their silence more decisive than shouts, their faint X-ray glows eliminating 3/4 of what we thought possible, teaching us stern lessons about the stiffness of matter. We looked at the triple system, PSR J0337 plus 1715, where a pulsar ticks with exquisite precision, while two white dwarfs circle it, testing Einstein's equivalence principle and finding no cracks, confirming that relativity still holds, even here. We connected those results to our Earth-bound colliders, where quark gluon plasma splashes into being for trillionths of a second, giving us hints of the states neutron stars may sustain for millions of years. And through it all, we held the awareness that neutron stars stand at the edge of physics, the crossroads where general relativity and quantum mechanics must one day meet. Now, as we let the story close, the details soften, the metaphors blur, and what remains is a feeling more than a conclusion. Neutron stars are reminders that the universe holds thresholds, that matter can be pressed beyond recognition, yet still find a way to exist. They are mountains with hidden heartbeats, lighthouses that tick with the rhythm of collapsed suns, laboratories where nature experiments in silence. They are questions written not in books but in pulses and waves, carried across light years for us to receive. And here, at the quiet end of our journey, you need not hold all the details. You need not remember the names of hyperons or the precise value of a limit. It is enough to carry the images. A teaspoon that weighs as much as mountains, a lighthouse beam sweeping across the sky, a rope stretched until it snaps, a room rearranged with strange furniture, a star humming with a chorus of bossons, a mountain with a faint heartbeat hidden inside. These images, soft and steady, can rest in your mind like stones in a stream, their edges worn smooth by time. So take a breath and let the night around you become quiet. Imagine the stars above, far beyond clouds or city lights, each one carrying its own balance, some steady like our sun, some collapsed into neutron stars, some gone altogether into black holes. Imagine that among them are hearts we cannot yet read, cores we cannot yet describe, but that still, across the distance, they send us their whispers, waiting for us to listen. And with that, our exploration has softly ended. Time flows forward, but tonight we've slowed it, drifting into the still heart of stars, resting for a while in the balance between known and unknown. May sleep find you gently, and may the questions linger as dreams, carrying you across the quiet spaces of the universe.